All right, let's get started. So welcome to Introduction to DirectX Raytracing. While you were filing in and before I started, I was showing a number of live samples, tutorials that you can actually download online and play with, and we're going to talk about a little bit in this course. And so these are things that you're going to be seeing, and they were running live on this GPU up here. So in this course is being live streamed, so photography and recording is encouraged for those of you in the audience here today. Resources for the course are on this webpage, intro to dxr.cwyman.org. So again, welcome, and hopefully I don't have to cover this, but let's ask, why are we here? Why do we have this course? And the key is that Microsoft announced DirectX Raytracing at GDC earlier, and I don't know if yours did, but my Twitter feed blew up as a lot of people learned and relearned and tried and retried ray tracing, and I saw this image I don't know how many times on my Twitter feed. So I showed it to you again, here before we started running live. And so what we have now with DirectX Raytracing is we have a widely used API that has ray tracing support built in. And this is great. I mean, coding in this is great. It allows you to have straightforward sharing of GPU resources. And as you've seen this week and at GDC, there's a number of compelling demos that suggest that you can actually use this in real production. Now, of course, I do want to caution you that we're not yet at full path trace renderers, and I hope some of you in the audience and some of you on the live stream might help us with the research that we need to actually make this usable everywhere in every game and everywhere else. Right now, we only have enough computation for a few rays per pixel, as you saw with those demos as I was moving around. And so you might get something like this on the left, where it's quite a bit noisy, and we'd really like to get something more like what's on the right, fully converged. So we need some research and additional research beyond what's already happened to reconstruct from low sample counts. And of course, yesterday we had hardware acceleration announced. So let's talk about the course goals. So if I think about who's sitting in the audience, I think there's probably roughly two classes of people. There's people who might be students, faculty, first-time SIGGRAPH attendees who have little or no DirectX experience. And there's also, I see a number of you, game developers and other people who have lots of experience in rendering who might be asking, well, what does ray tracing mean for my raster application, and how do I think about integrating it? And so these are two very different audiences, and I had a hard time thinking about putting this course together in a way that satisfied both. So the plan is, in the first half of the course, I'm going to aim and target towards those in the first category, those with little DirectX experience, who might be asking, how do I get started with ray tracing, and maybe what is ray tracing? And so ideally, I'm going to give you an introduction to ray tracing. Pete's going to do that, and hopefully help you understand the new DirectX shading and the mental model of GPUs in the ray tracing pipeline that we now have. And then I'm going to walk through a number of incremental shader tutorials that you can download the code, and actually much more extensive tutorials online to help you build a simple path tracer. This is very simple. It's not optimized in any way. I don't pretend it's optimal code. It's there to get you easy access to a ray tracer, a path tracer that you can experiment with. In the second half, we're going to go lower level and focus on the second part of the audience. We're going to talk about the lower level C++ host side API and help you understand the basics of how DirectX has changed for ray tracing. Understand the mental model for programming, the CPU for DX ray tracing, and share experiences in integrating DXR into existing raster pipelines. So that's sort of my course goals. So who are we? Well, I'm Chris Wyman. I'm a principal research scientist at NVIDIA. And before joining NVIDIA, I was a faculty member for 10 years. So Pete Shirley, who's going to talk next, is a distinguished research scientist at NVIDIA. You probably all know him as the author of multiple widely used textbooks, including Ray Tracing in One Weekend, which is where that sphere scene came from. Sean Hargreaves is from Microsoft. He's going to talk about the low-level API part. He's a principal development lead of Direct3D at Microsoft. He's worked on numerous games, developed assorted APIs both at and prior to coming to Microsoft before working on Direct3D. And Colin Barret-Brisbois is a senior software engineer at Seed Electronic Arts. He was previously at Warner Brother Games and has an impressive list of games to his credit. He does a lot of blogging and shares his ideas at GDC, i3D, HPG, SIGGRAPH, and elsewhere. I highly recommend you look at his slides for his HPG keynote this year. So today's schedule is, I'm welcoming you here. Pete's going to give an overview, what is ray tracing? Then I'm going to switch back and talk about what are the basics of DirectX shaders for this new ray tracing pipeline, and then walk through some tutorials in a sort of incremental step-by-step fashion. We'll have a break, which we might also use for Q&A. And then afterwards, Sean will talk about the introduction to the host side code, after which Colin will talk about his experiences integrating DirectX DirectX ray tracing into existing raster pipelines. And then we'll have some more Q&A. So before I hand you off to Pete, some thoughts. So real-time ray tracing has always been 5 years away, and I've always been a skeptic it would actually happen, and now I'm actually convinced it is happening. So, of course, we're not going to match film quality renderings anytime in the near future, and so we still need some R&D work here. And I think this is really important for those of you who are thinking about what to do next, that we need to think about how to develop things like hacks that make the image look good in 16 milliseconds. You know, hack is not a derogatory term here, like those used commonly in all sorts of raster applications today. What are those same techniques in the ray tracing world? And again, a reminder, all the images I've been rendering here are rendered from the tutorial code that's available on the web page. Of course, these are converged, not at 1 sample per pixel. Putting on my NVIDIA hat for a moment, we're talking a lot more about ray tracing throughout the week. We have a sponsored session later today and tomorrow morning, and things at the Expo booth. We also have some resources online, including research code for some reconstruction filters, in addition to more polished solutions on our GameWorks product. One last plug before I get off the stage. There's a call for proposals for ray tracing gems. If you're doing ray tracing stuff and want to publish your work in this book, please see the information here. All right, thank you very much. I'm going to pass you off to Pete Shirley, who's going to give you an overview of ray tracing.
Thank you. My agenda in this talk is to let you know that the terminology about ray tracing is a little messed up. There's 40 years of literature, and we haven't been very good about being consistent. And so saying you do ray tracing is kind of like saying, I do addition. You know, it's a primitive, but sometimes in some contexts it means something much more specific. And so I want to give you a bit of a decoder ring during this talk as well. I don't know how to use Chris's laptop. There we go. So this is the paper that really gave ray tracing its entry into SIGGRAPH and graphics in general. I was in college, and this paper switched me out of physics into computer science. And I reread this in preparation for this talk, because this is what people often mean, probably as a default, when they say ray tracing, is this paper. The amazing thing is this paper is not very dated. If you read through it, there are very few cues that it wasn't written in the last year, and this basic code that Turner Whitted wrote 40 years ago is pretty much what Chris was showing with a few changes, which I will talk about. The quiz for you guys is there's exactly one mistake in this paper. I won't say what it is. But if you find it out, I'll tell you if you're right. It's a small one. Chris, I really don't know how to use your space. Thank you. Okay, so what I just showed you is Whitted ray tracing. So when someone says ray tracing, they might mean Whitted ray tracing, which is his algorithm, and it's shiny stuff. But then everybody changed their ray tracer 4 years later when Rob Cook, out of Lucasfilm at the time, Pixar now, did these amazing soft shadow pictures. And he basically started calling RAND in the ray tracer. That's the change. If you call RAND in the ray tracer and there's not much change, people call that Cook-style ray tracing or distribution ray tracing. And then Kajia came along and said, you know, you can also call RAND on the diffuse surfaces and get diffuse interreflection. People call that path tracing, or they call it Kaguya-style ray tracing. And often they will leave off that modifier, and they're just talking about a very specific one of these families. And you can just ask them, which one are you talking about? People who do ray tracing all the time have to stop and say, what do you mean? And my field can take credit for that. We didn't clean up the terminology. We had 40 years to do it, but we didn't. So here's Whitted-style ray tracing. A ray comes in, it sees something shiny, it takes a specular bounce. There's this nice little formula, vector formula for the specular bounce. Here is Cook-style ray tracing. And what it does is it says, hey, when I hit a mirror, maybe I'm going to scatter around that mirror direction and make things fuzzy. And when I send a shadow ray, I will send it to an area of a source. I won't send it to a point source. It's a very brute force approach, and it needs more than 1 ray per pixel, which is one of the big costs and why this didn't take off for a long, long time. So note, this technique was invented in the film industry, and yet it took 20 years before the film industry started using it all the time. So there was simply a speed gap. That picture is actually from 1984, and even today it holds up. That's an impressive picture. So people often allude to this, the 1984 picture. That's a good exercise, just try and duplicate it, because it's got a lot of things going on in there, but you only have to implement an infinite plane and some spheres. One reason it looks so rich is there's a good environment map. And so all the reflections in the balls are into an environment map, not a model. And then in Kaguya, really, if you take a Cook-style distribution ray tracer and modify it into a Kaguya-style ray tracer, all you really do is call rand on the diffuse bounces. You change 2 lines of code. But it's kind of a different mentality in that now the rays are incredibly divergent and the program is super slow. You need a lot of rays per pixel. And so this has taken off even more slowly. Denoising has been a huge thing for that. So here's an example of denoising, which it's been an idea that's floated around the graphics industry for a long time, but it's only really started being used in production recently. The movie people have been using it for a while, particularly Disney. And it works implausibly well. I think this is the free lunch that has helped bring ray tracing quickly to the forefront lately. Is everyone assumed you need a lot of rays per pixel. And it turns out denoising is easier to do. I shouldn't say it's easy. It works better when done right than anyone would expect. I personally still find it surprising that the image on the left can be turned into the image on the right with a time sequence, and that can be done interactively. So there's kind of a convergence now of the hardware is getting a lot faster at tracing rays, and this algorithmic improvement by the industry has just given you an extra factor of 10, just like that. And factors of 10 don't come along very often anymore. So one thing is, okay, is ray tracing going to take over the universe? And I would predict no. And the reason is these are both perfectly good ways to get stuff on the screen. And rasterization is pretty amazingly fast. And we're very good at it. And what it basically does, and most of you are familiar with it, it throws triangles at the screen, and then they stick if they're visible and in front. And the Z buffer keeps track of the visibility, so you can do it in any order. Very clever idea back in the day. Ray tracing just is an equally brute force algorithm that just takes pixels and throws them out into the environment. It says, what triangle do I see first? And they're duals of each other, really, and they're not that different. It's really like, what order does the loop go? Computationally, they end up being quite different, both in speed and how they walk through the computer. But when you, and this is a slide Chris gave me because he understands rasterization a lot better than I do. And so, like, wrapping your mind around what are these really bringing to the table for a visibility problem? So I'm actually just going to zoom in on one of these. You can read this slide, but there's a lot of complexity here. I want to go to the acceleration structure. Neither of these algorithms ends up being simple in real life, because in a game engine, you might have a hierarchical z-buffer or some culling volume. You're going to have some tree somewhere that makes your program all complicated. So it's really not simple like a rasterizer, like just a straight z-buffer. And ray tracing sounds all elegant. You loop through the environment, but you need to stick a tree on that thing too. And then the model changes frame to frame, so that tree needs to change. And really, under the hood, ray tracing and rasterization both get complicated when you actually try and make it fast. And they have different trade-offs in when one is good at something and when another is good at something. The thing I've been experiencing lately is if you have a very weird set of pixels you need to compute, like in some warped HMD, then ray tracing is a very natural way to go. If you can have some very structured way you're querying visibility, z-buffer's good. And that will probably remain true. Now you have, it's not that ray tracing will replace z-buffers, it's another tool in your toolbox. Okay, this is the part of the talk that I think is most important if you have written a ray tracer and kind of know your way around, so you're kind of checking your phone during this part of the talk. Or if you're brand new and people just present you, here is array. Array is just a 3D line, and you can represent it any way you can represent a 3D line. And pretty much 3D lines are not taught except to pretty hardcore engineers. Like computer scientists are rarely taught what are all the different ways to represent a 3D line. In high school, if you're from the US, you probably saw 2D lines, and that was y equals mx plus b. Can I just use that for array? Answer, no. So implicit equations like that, the dimensionality of the object needs to be one off from the dimensionality of the space. An array is a 1D object. It's 1D in that you walk along it and say, how far along this array am I? You need one number. Space is 3D. That doesn't work. You could do it geometrically. I take two planes, which I can write implicit equations for. I intersect them. The intersection of two planes is a line in 3D. Some ray tracers do this, that for intersecting certain types of patches, that the mathematics works out well. Pretty uncommon. Much more common is to blend points in 3D and blend them in a way so you're constrained to a line. So first, let me just talk about points in 3D. We usually represent that as a direction vector from the origin to a point. So you have three numbers, you declare a vec3 or something, depending on what your infrastructure is, and you say, okay, I can take some third vector, C, if I have vectors A and B defined, and I can just do a linear blend of them, like 10 times this point and 32 times that point. Any two numbers you want, and that will give you a point in the plane of A and B. So any point in the plane of A and B can be a combination of a linear combination of A and B. If you constrain that combination to be a weighted average so that the two weights on A and B sum up to 1, then you're constrained to the points between A and B, which is a line. So this is one way you can just map out a line segment in 3D, which you often have to do for many graphics programs, and many of you have probably done this before in various contexts. A key thing is, there's nothing that says those weights both have to be positive. So you can throw in a weight that's, say, like 2 for B and -1 for A, and it will allow you to migrate that one of the weights. Since they add to 1, you really only have a one-dimensional thing here, which I've written as t. As you modify that t from -infinity to infinity, this point just walks along the ray. When you plug in 0, it's at point A. When you plug in 1, it's at point B. When it's between 0 and 1, it's on the segment between A and B. When it's more than 1, it's past B. When it's less than 0, it's behind A. And so there's a certain implicit directionality to this line if you think of positive as progressing, though really it's just a parametric line equation for a line in 3D. Array sometimes, and I remember I said when you say ray tracing, I'm not sure what you mean unless you qualify that. Sadly, that is also true of array. So when someone says, I have array, it might mean several different things. In this case, array is a half line. So stuff behind A, in other words, T that is negative, aren't part of the array. And that as a default is probably what people mean. And then there are plenty of variations of this in various graphics codes. So I could say, well, I'll just store A and T, and then I'll have this direction vector from A to B that'll be B minus A. So you have 1 point, 1 vector. All of these are valid ways to do things, and I'd say just the key is to have a really solid understanding of which one you were using and comment it. Because this stuff, to this day, gets me into trouble, especially that last bit. Is the direction vector a unit vector in your ray tracer? If you can assume it is, then certain functions that take it can be more efficient. But then you have to do some bookkeeping to make sure you manage those unit vectors. And so here are just some examples of regions on the ray based on what the T values are. In the first one, it's going to be most of the half line. And notice that it starts at 0.05 out there. Often rays originate on surfaces, and when one of the points on the surfaces do a ray intersection and you hit the surface there, you get trouble. And so people often put in a fudge factor. But sometimes they don't. It depends on the ray. So again, context is really important for managing these little details. In the middle red case, the points are only between A and B, so it's essentially a line segment. And then the green case is just a weird thing where for some special purpose you might do this. These do come up. This isn't like some almost never happens. Often you take advantage of your knowledge of the geometric meaning of those intervals of T. So what do we do with rays? We do a lot of standard queries. I'll just go through the first one. I mean, you can read down those. But the first one is, hey, does this ray hit anything if I just send it forever? Usually that's a shadow kind of query. You don't care where you hit it. You don't care what you hit. You just want to know if something is visible. Or if it's visible within a meter, maybe you're doing ambient occlusion. So there are often rays like that that are occlusion rays. But then sometimes you want to know, what did I hit? Tell me what I hit and where. And then there's a peculiar thing that is not done very often, but sometimes it's like critical for what you need to do. You want a list of everything that array hits. And you might have to build that yourself, depending on your API, or you might it might give it to you. If you ever want to do a CSG program, this is an amazingly elegant way to do it. Can be slow. So how do you make rays faster? And the bottom line is, array is a search. Array intersection with the model is a search. I have a million triangles, I have one ray. Which of those million triangles do I hit? And computer scientists, to a first approximation, have one invention, a tree. And we turn order n algorithms into order log algorithms. This is no exception. In practice, it is log n, but it's not guaranteed to be. So if you ever see yourself with amazing slowdowns, your tree is probably the culprit. And the bounding volume hierarchy, there are lots of different acceleration trees used in ray tracing. The bounding volume hierarchy has kind of one in practice. So it's just like quicksort is the sorting algorithm you go to, and it's probably some variant of it is implemented in your libraries. Same thing for BVHs. So if you read a bunch of ray tracing literature and you're trying to get up to speed, and we all have a finite amount of time, just go read the BVH stuff. The interesting thing is, theoretically, people don't fully understand why they work as well as they do or why we build them the way we do. So if you're a theory type, this might be worth digging into. I've tried, so I can tell you it's not low-hanging fruit, but I'm not a theorist. Okay, I want to close and take a little more time on this slide. This is important for both the beginners and the veterans here. Let me just take a quick query. Who has never written a ray tracer? Maybe 20% of you. And who has never written a complex Z buffer-based program, like an OpenGL or DirectX, who's like a novice? Okay, not as many of those. Most people in here have written at least a rudimentary ray tracer and have some Z buffer experience. There's a cultural thing about ray tracing that is evolutionary, I think. So back when I was in school, if you just personally had not much interest in speed but really liked pretty stuff, you became a ray tracer. And if you liked stuff to move rather than going home and coming in the morning, you became an interactive programmer. And the interactive programs didn't look very good. And then along came shading languages, and people said, huh, I can actually use this Z buffer for all sorts of things it was not intended for, and did amazing hacks. And the pictures look friggin' awesome. And every one of those little hacks is quite clever. And when they came along, you're like, wow, that was clever. No such evolution ever happened in the ray tracing literature. We were like, well, it's already slow. I'll just implement one of those, Witted ray tracer, Cook ray tracer. Yeah, I could probably make it 30% faster. Maybe I'll get a grad student to do that or something. Then along came, various ray tracing libraries that did that for you. But using the rays themselves to do something very clever in the spirit of the Z buffer community, that really hasn't happened. So we're in this very surprising state in graphics, which is a very mature industry, where there's this new tool that's been put in your toolbox. And the army of clever people that have specialized in doing cool shaders, like half the stuff at Shader Toy, I'll stare at it for an hour and not understand why it works. It produces this amazing picture. That has not really happened with ray tracing. And that there's like a 2-year, I'd guess, based on past history, of lots of time for clever people to make this stuff work a lot better in ways that it wasn't designed for. So just like shading languages, the people that did those originally, they did not foresee the crazy stuff that was done with that. And my hope is that that would be true of ray tracing as well. It's not an algorithm, it's a hammer. Big hammer. Thank you.
Thanks, Pete. That was great. Maybe. There we go. All right. So now I'm going to walk in and give you an overview of the HLSL shaders and walk through tutorials, and we'll do that in a little bit. Again, thanks, Pete, for giving a nice overview of the basics. And now you might be asking, how do I do it in DirectX? And of course, instead of using DirectX, you could start from scratch. You could go write a CPU ray tracer. There's plenty of resources, really good resources out there. And you could write your own GPU ray tracer, which can be tricky and a bit ugly for those of you who've tried to do it. You could also use vendor-specific APIs. They hide a lot of this ugly low-level details on the GPU, but they don't scale across vendor, and they're hard to interact with raster sometimes. So of course, you're all here to hear about DirectX Raytracing, and so that's the goal today. So again, as I said before, now ray tracing is part of a widely used API, namely DirectX, which allows you to share resources with no copying between raster and ray tracing. No copying, no overhead of different APIs, nothing like that. And it works across vendors, either via vendor-supported software and hardware, or there's a standardized compatibility layer that runs on DX12 class GPUs. And so just an overview of modern graphics APIs for those of you who may not be familiar. You can sort of, in a very high level, 10,000-foot view, split it into two main parts. There's code that runs on the GPU, which are sometimes called shaders, and it runs parallel on the GPU, but you program it in a very simple-looking way. It looks serial. And then there's CPU host code, the API itself, which it's often like things, the DirectX API, which it sort of controls everything else in the system besides what's going on in the GPU. And the talk I'm going to give you now is going to focus on the GPU side, the shaders, and after our break, Sean's going to talk about the host side here. So for those of you who haven't been programming shaders all your life, what are they? So they're developer-controlled pieces of software that control the graphics pipeline. These are the parts that aren't automatically managed by the graphics API, the driver, the hardware, and other things. And really, this is where you get to write your GPU code. So these are usually written in a C-like high-level language. In DirectX, this language is called the high-level shading language, HLSL. And these shaders can either be used to represent complete GPU tasks, for instance, with a compute shader, or they can be used to represent some subset of a more complex pipeline, for instance, the vertex shaders in today's graphics pipe. Now, before I go and talk about the ray tracing pipeline, let me just do a very brief overview of what DX raster looks like today. So in rasterization, you send your geometry data, your vertex data, down from the CPU, and you run through vertex shader, which you can think of it kind of as it transforms it into the right relative location to the camera. Then you run these tessellation stages, which combine these vertices together into triangles and dice them up into smaller triangles. After which you get to run a geometry shader that computes things on a per primitive basis. Maybe for some reason you want to compute a normal of these new tessellated triangles. Would be a very, very simple example. After which you go to the rasterizer, which here is green because it's done by special purpose hardware or perhaps software behind the back, and you don't get to control everything, you just get to control some parameters of this. And then the rasterizer takes these triangles and converts it into fragments or pixels on the screen, after which you run a fragment shader or a pixel shader to do your shading to compute a final color. After which you output this to the frame buffer, and again, this is done using some sort of special purpose hardware to hide things like compression and different image formats. And so if you squint a little bit, this pipeline kind of looks like this, right? You input a set of triangles, some code runs to transform this into a set of displayable triangles. You run some special purpose stuff that converts that to pixels, after which you get another controllable shader to generate colors, and then you output to a final image. And so if you think about that, you could kind of phrase ray tracing in a similar way. So what might this similar ray tracing pipeline look like? So again, if you squinted, and again, this is a very simplified representation. If you squinted, you might want something like this. You take a set of pixels as input, you run some code to generate rays, to figure out where what rays correspond to what pixels. You run some specialized stuff that intersect those rays with the scene, and then you get to shade the hit points. And then you output that to your frame buffer. So in some sense, this looks really similar to that 10,000-foot view of the raster pipeline, except of course, algorithmically, ray tracing gives you this advantage that you can recursively spawn rays in your shading and go back through your acceleration structure to get multi-bounce effects. All right, so now let's actually get into the meat. What sort of shaders do we have in DirectX? It turns out this very, very simplified pipeline that I invented up there, that's sort of what it looks like. I'm pretending that's what it looks like. It's actually split into multiple different shader stages. There's a ray generation shader. This is going to run once per algorithm or per pass. And this is what starts your ray tracing. So this is where you take your pixel information and turn it into rays. Then there's a new shader stage called an intersection shader. And this is how this defines how rays intersect the geometry. How do you intersect a ray with a triangle? How do you intersect a ray with a sphere? How do you intersect a ray with a Bezier patch? You do that by writing different intersection shaders. Then, when you're tracing your rays, what happens if you miss? Well, you can control that using your miss shader. What happens when you hit? Well, that's controlled with your closest hit shader. And this closest hit shader, if you want to think of it at a very, very high level, is similar to your fragment shader. This is usually where you're doing shading computations. And then there's an any hit shader, which is run once per hit. And I just like to make a note here. As you go to use more advanced usages of this, please read the spec. The definition of any may not match your expectations. These collections of the miss shader, closest hit shader, and any hit shader define the behavior of rays. And you can have different rays in your program. As Pete was talking about, you might have a shadow ray, you might have a color ray, you might have a primary ray, you might have other sorts of rays. And so you can have multiple of these shaders depending on how many rays you have. Now, something I'm not going to talk about today, there's actually a sixth shader, a callable shader, which allows you to call one shader stage from another, essentially branch your shading stages. And I'm not going to talk about it further. You can read about that in the spec if you're interested. All right, so let's take this very simplified pipeline I invented and actually turn it into the real DirectX pipeline. So again, I said we start with a ray generation shader. So this is where you launch new rays, and in HLSL you do this by calling the new trace ray intrinsic. And then it goes into sort of this abstract ray tracing happens blob, and you come back, you get a color, and you can accumulate that into your final image. So now let's actually look and zoom in to what happens in this nebulous ray tracing stage. So a good mental model might be, first we traverse our scene to find what our ray hits. So now we're thinking about an individual ray, it's tracing through the scene. What geometry do we hit? So we go through this bounding volume hierarchy, or whatever your acceleration structure is. And if you find a hit point, you'll shade it with the closest hit point, or with the closest hit shader. If you don't find any hit, you'll shade with the miss shader. And so this closest hit and mini hit shaders could be thought of as your shading stage in raster. Now let's look through the traversal loop. The first thing that happens is your ray goes in and goes into some green box here, some opaque acceleration process by which the GPU, the driver combined find out what sort of objects might be potential hits for your ray. If you don't find any, you immediately leave this loop and go run your miss shader. If you do hit something in your bounding volume traversal, you get to run this intersection shader, and this allows you to control, do you intersect this particular piece of geometry? Maybe it's a sphere, maybe it's a triangle, maybe it's something else, a Bezier curve. In DirectX, there is a built-in triangle shader, so you don't have to write a triangle intersection shader, but for anything else, you're on your own. You get to write custom software. If you don't hit anything, right, you run this intersection code and you say, nah, I didn't hit, sorry. You go back into this acceleration structure and keep going. If you do hit, but it's not the closest one, you also go back into the acceleration structure and keep looking for potential hits. So you leave the intersection shader and you do find the closest hit, what happens? Well, you go over here and check whether it's opaque or not. If it's not opaque, you run the any hit shader. And again, I'll put my little symbol here in that I didn't really name this. So in order to run the any hit shader, it has to be the closest hit you've seen so far, and it has to be flagged as not opaque. If it's not, so in the any hit shader, you can ignore it. For instance, if you're doing alpha testing and you find a texture that's transparent, you say, this isn't a real hit, keep going. And you can cycle back into the acceleration structure loop. Otherwise, you update your closest hit and keep going, because you might have another hit that you haven't found yet that's closer. So you keep cycling through this until you no longer hit anything, at which point you go over here and you ask, any time through this loop, did I hit anything? And if the answer is no, you run your miss shader. If the answer is yes, you run your closest hit shader, after which you leave the trace ray loop and you get your control back wherever you launched your trace ray. Okay, so in summary, the high-level view of DirectX ray tracing shaders. If you want to control where your rays start, you should do that in the ray generation shader. If you want to control how your rays intersect geometry, that should be in your intersection shader or in one of your intersection shaders. If you want to control what happens when your rays miss, that should be done in your rays miss shader. If you want to control how to shade your final hit points, that's probably going to be in your closest hit shader. And if you want to control how transparency behaves, you should probably see your any-hit shader. All right, so what goes into one of these DX ray tracing shaders? So starting a DXR shader, you need to have an entry point, right? Just like in C, C++, you have main. In DirectX, shader points can be arbitrarily named. And so in this case, I've named it pinhole camera raygen. Right above that is the HLSL attribute. So this specifies that this is a ray generation shader. So the compiler knows, and it knows how to connect that up with the host side. Other shader types look like this. An intersection shader, you tell it it's an intersection shader, and you give it the name. It's any name you want. In both these cases, there's no parameters required for these shaders. For a MIST shader, you tell it it's a MIST shader, and this requires information about your ray so that you can pass return values back. For instance, your payload might have a color. An any-hit shader looks something like this. You define it as an any-hit shader. You give it a payload and also where you've hit your surface. So the attributes tell you where you've hit your surface. And then the closest hit shader looks like this. You also give it your payload and where you've hit your surface. So the ray payload is user-defined, so you can control what goes in here, and it depends on what you want to do with your ray. A shadow ray, you might just want to return a binary thing. Did I hit or not? A color ray, you might want to stash a color in here. And for more complicated rays, you might want to do more interesting things in there. The intersection attributes are also, these are also user-defined, but they define, they correspond and transport data from your intersection. So you find out where you hit the surface into your closest hit shader or your any hit shader, where you might need to know where you have intersected something in order to shade it. So what's a payload? As I said before, it's arbitrarily user-defined and user-named structure, and it contains the intermediate data needed for your ray tracing. It's passed along with the ray. You can think of it as piggybacking along with each ray. If you're not familiar with HLSL, and you're starting to see this code up here, HLSL has a bunch of built-in data types, boolean, uint, float, and you can also put them into vectors like this float3, which is an array, a vector of 3 floats. You can also do this with matrices, 4x4, up to 4x4. One thing to note is you should keep this ray payload as small as possible, because if you make it large, things happen like you spill out of GPU registers into memory, and that will slow you down quite a bit. So a simple ray might look like this, right? You have a MIST shader, you pass in a payload, which has this color that I defined up there in my structure, and in this really simple MIST shader, I'm returning blue. And then you might have a closest hit shader like this, and this is also a very simple closest hit shader, I'm returning red. This actually defines a complete ray type, which will return blue when you miss and red when you hit. So what are these intersection attributes? These allow you to communicate between your intersection shader and your any hit and closest hit shaders. And they're specific to each intersection type. There's a built-in one for triangles. But if you want to define a sphere intersector, you have to define intersection attribute structure for your spheres. The built-in one looks something like that. It has a couple a float 2 with barycentric coordinates where you hit the triangle, and that's what you're given for shading. Potentially, this is just me inventing things. You might look, your sphere attributes might look like this. You might have a theta phi. And you might have a float 3 if you're doing a volumetric intersection. I'm not claiming these are right. These are just explanatory. You might imagine custom attributes looking something like that. Be very aware that these attribute structures are limited in size. Currently in the spec, I believe these are limited to 32 bytes. So you've got 8 floats to store intersection attributes, and you should make that as small as possible as well. So simple example. Let's think if you haven't written DX code and HLSL, what else? And even if you have, what data do you need on the GPU to shoot rays? Well, you need some place to write your output. So let's define an output texture, a read-write texture, a UAV. And in this case, it's called outtext, and it is a float 4. So where are we looking? In ray tracing, we have to put our camera someplace. So we need some information about where our camera is, and you need to pass this down to the GPU someplace or somehow. In this case, I've defined a constant buffer with a camera position and a UVW coordinate frame for this camera. And we need to know some information about our scene, like what our acceleration structure is, so we can intersect it. So that's enough to get you started with a really basic DXR shader. You also need some more complicated information about how to shade your scene, and this will be different from framework to framework or renderer to renderer, depending on how you're storing your shading and material values, and even your geometric values on the GPU. And so you can look at the tutorial code online to see how I do it, but in your renderer, this will change. So let's walk through a really, really simple DXR ray generation shader. So in the upper right, in that small text, that is the CPU, GPU data declarations that I did on the last slide. So here's my ray generation shader. The first thing I'm doing here is asking what pixel am I? This uses the new intrinsic display rays index, which says where on the screen, where on the screen am I? And then the second one says how many pixels in total am I launching in this ray launch, and you query that with another intrinsic dispatch rays dimensions. And then I'm going to take that information and convert it into a ray. So I find the pixel center for my current pixel in the 0 to 1, convert it to normalized device coordinates, similar to raster somewhat, and then using my camera matrix, I turn that into a ray that goes through the center of the pixel. And so if you want to squint a little bit, collectively these few lines take a pixel ID and turn it into a ray dimension, or excuse me, a ray direction. Once I have that ray direction, I can set up my ray. To do this, I'm going to use the new DirectX data structure called RayDesk, which has a couple different, this is the built-in type here. It has an origin, a tmin, a direction, and a tmax. So if you want to define it in curly braces, that's the order you have to define it. Here I'm passing the camera position down as the origin. That makes sense. This ray direction that I just computed through my pixel down as the direction. Tmin of 0 and a tmax of a big number. You could use float max here. I was too lazy to type all those characters. Tmin here is 0. I'm starting at the camera. There's no problems self-intersecting here because I'm on the camera. There's no geometry, so I don't have to worry about any epsilon value. And Tmax, so I'm going off as far as I can in the scene to see if I intersect anything between those two values. That's what's going on there. I need to set up a ray payload, right? This is going to contain the color that gets returned. And so I define the simple ray payload that I used on a prior slide as an example that just has a color, and I initialize that to black. Then I trace my ray. Now I'm going to step through this here. Trace ray is a new HLSL intrinsic. Oops, sorry. The first parameter here is the scene acceleration structure. Which acceleration structure are you tracing rays against? And this needs to be passed in from your host side code. And you can see either the tutorial code, or Sean will probably talk about this a little bit in his section. The next flag controls any custom behavior that the ray might need. In this case, there's none. I'm using the default ray behavior. The next parameter is a little confusing. It's an instance mask, and by default, 0xFF tests all the geometry. That's probably what you want for basic things. If you have more complex things, like you don't want to test certain classes of geometry, you might give them a mask, and then you can easily skip that geometry with this instance mask. The next three parameters define which shaders you're going to use while traversing through this. So which mist shader are you going to use, which closest hit shader are you going to use, which any hit shader are you going to use, and which intersection shader you're going to use. Oops, sorry. The first one, which I've labeled here hit group, is a collection of intersection shader, any hit shader, and closest hit shader. And These are defined when you initialize your ray, you initialize your code on the CPU side, and there's integer IDs. The next parameter is the total number of hit groups that you have defined, and the third parameter there is which MIS shader you're using. Then you pass in the ray, which I defined up here, and the payload, which I defined over here, and that completes your trace ray. You go off and trace your ray, things happen, it comes back, and you say, all right, grab that payload color and stuff it out to my texture. If you combine this with this really simple red-blue shader, where you hit blue, if you hit, you get red, you miss, you get blue, you now have a complete DXR HLSL ray tracing shader that will give you a red if you hit and blue if you don't. Okay, so now that I've given you a simple high-level view, well, actually a low-level view of what these shaders do, let's actually ask a little bit more specifically, what sort of features do you have available to you here? So you have available all the standard HLSL data types, texture resources, et cetera, and I would refer you to the Microsoft documentation if you don't know what those are. You have the standard built-in HLSL intrinsics for math, things like graphics, spatial manipulation, 3D math, square root, et cetera, trigonometry, vectors, normalized length, matrices, and again, I'll refer you to the Microsoft documentation if you're not familiar with all this already. Then we have new intrinsic functions specifically for ray tracing, and those I do want to walk through because those are interesting. So the first set of new intrinsics that we have are related to ray traversal. So you've already seen trace ray. This is a ray, this is what spawns the ray. You can call this from a ray generation shader, a closest hit shader, or a MIS shader, which allows you to do recursive ray tracing. You cannot launch it from an intersection shader. You're in the process of intersecting your existing ray. You can't launch one there. And you can't launch it from the any hit shader. Report hit is what you use in your intersection shader to say, aha, I found one. Go shade it. In the any hit shader, you can ignore a hit that you found in your intersection shader. Basically, hey, this is transparent. I don't actually want to do final shading on it. Keep going. That's what ignore hit allows you to do. And accept hit and end search is like, oh, I found the one. I'm done. Stop. Go shade this one. Don't keep traversing. And that allows you to speed things up if you have a type of ray where you can know that in advance. All right. Another class of built-in functions are the ray launch details, and you've already seen these. There's dispatch ray dimensions and dispatch rays index, which allow you to query, given your current launch of rays, where are you in that grid of launches? And you can use this in any shader here. Ray gen, intersection, any hit, closest, or miss. And so if you launched a full screen 1920 by 1080 pass of rays, you can get 1920 by 1080 back from your ray dimensions and some number between 0 and 1920 and 0 and 1080 with your index. Another category of new built-in functions there's just one, is hit-specific details. It gives you information about your current hit, in this called a hit kind. This is available in the any hit and the closest hit shader. That's the only place you're dealing with hits. And this is actually user specified. So in your intersection shader, you can specify what sort of hit kind you have so that you can reason about that when you get to your shader. And in the case of triangles, there's two built-in hit kinds, front-facing and back-facing. So if you want to shade differently based on which side of the triangle you hit, you can do that. And you can query that with the hit kind function. Another class of new built-in functions are for doing ray introspection. So properties about my ray. So you can find out what your current T value is along the ray, what your minimum value is, which was passed in as a parameter to trace rays, what your flags were, which was also passed in as a parameter to trace rays, along with your ray origin and ray direction in world space, which also were passed in as parameters of trace ray. So basically, these functions query parameters that you pass to trace ray and also where you are currently on the ray. There's another category of built-in functions that allow you to do object introspection. What object am I currently interacting with. So you can ask, what's the instance index, instance ID, primitive index, along with transformations from your object space coordinates to world space coordinates, and your ray origin and ray direction transformed into object space. And these are available only in the intersection, any-hit, and closest hit shader where you have both a ray and an object. So they're not available in the MIST shader. All right. So that was sort of my high-level overview of HLSL DirectX Raytracing shaders. I thought I would make this a little bit more concrete by putting together a bunch of tutorials. And these tutorials you can download from the web page, which is there, and some of which you saw before the course started running on this machine up here. And I want to walk through these a little bit step by step to sort of help you understand how simple this actually is to build a ray tracer once you have the host side code encapsulated in a way that you're just writing HLSL basically. So what are the goals with these tutorials? So the code that I'm providing online is they're there to provide a simple abstraction to help you get started. I don't pretend these are well written or well optimized. They're written for clarity, not for performance. I'm providing code that you can use as a starting point. And what I hope to show you is that DirectX Raytracing can actually be straightforward. If you encapsulate all the host side details, you can actually get up and running with DXR in 10 or 15 minutes. Hopefully, this will allow some of those of you who might be students, et cetera, to do some quick experiments with hybrid ray raster techniques. In addition to encapsulating DirectX Raytracing, I've also encapsulated DirectX Raster and allow you to communicate between them in a very simple, straightforward way. So hopefully, this allows you to also get started with raster if, for instance, you are not familiar with DX12. And I've also abstracted the GPU-CPU communication in a way that makes a lot of sense to me to help me think to code at the level that I think, which is perhaps more abstract than some people. So the tutorial code is structured into two pieces. The first piece, which I'm not going to talk much about except for a quick overview here, is a high-level C++ abstraction using a render graph style programming model. And then, of course, there's the standard HLSL DirectX Raytracing shaders, and these are mostly standard. There's one tiny detail that's different that allows you to access our internal scene representation for our tutorial. So this C++ abstraction, which again is not the point of this tutorial, but I'm just providing here to show you how easy it is to get started. This is a render graph. This is how you initialize one of your render graph nodes. You ask for the resources, the texture resources that you might need while doing this computation. In this case, this is the simple red-blue example from before. I just need an output texture, so I asked for the default output texture. That's what's going on there. Here, I'm creating my DXR ray launch. So here is the HLSL shader that I'm going to launch my shaders from, and you've seen examples of this already. These here are the names of the entry points, so the RayGen shader, the MIST shader, the closest hit shader, and the any hit shader that I'm going to be using during these during this ray tracing. This specifies the MIST shader. This specifies MIST shader number 0. With my abstraction, the first one you specify is number 0, the next one you specify is number 1, et cetera. This one specifies hit group number 0. Again, they're specified in the order in code so that you know which number they are. If you don't have a closest hit shader, you can skip it by not passing one in. If you don't have an any hit shader, you can skip it by not passing one in. You compile, build the internal data structures, and then you set your scene down there. When you render, your code looks something like this using this abstraction. You ask for your output texture, clear it, pass your variables down to GLSL. In this case, my variable that I'm passing down is a texture, and it's named gouttext in my HLSL shader, and the thing on the right is the texture I'm binding to it. And then I run my DXR launch, and that's how many rays I'm launching. In this case, I want to launch a screen size bunch of rays. So again, that's the C side. And let me be clear, this is not the focus of the talk. The tutorial goals here are quickly getting you started with GPU-accelerated ray tracing, and this hides the ugly DX12 stuff if you don't want to deal with that, and gives you an easy-to-use abstraction layer. It's not designed to expose advanced functionality. If you want that, you should listen to Sean talk after I'm done. If you want to use these abstractions, feel free. The code's online. Grab them and use them. I encourage that. So the focus for the rest of these tutorials is going to be the HLSL shaders that we need to write. So this is the same HLSL shader I showed you before, although I've simplified and reorganized it a little bit. Again, the name here I specified in my C++ code for the launch. My output texture is this texture that I also specified in my C++ code. And these values here, the camera position and the scene acceleration structure, are specific globals provided by our tutorial wrapper. We need a ray payload, and then this function here is a utility function that simplifies that 5 lines of mess that I had on the previous slide into a simple abstraction here. And again, you take a camera position and 3 vectors plus your position on the screen to get you a ray for your current pixel. These values here are the min and max distance to search along the ray. I'm using MIST shader number 0, which again I specified in that order in my code. I'm using hit group number 0, corresponding to my closest hit shader. And I only have one hit group, so that's that value there. The one non-standard bit is up at the top. I add this non-standard HLSL import ray tracing. This is actually from our Slang preprocessor, and the Slang language is actually a paper being presented this week at SIGGRAPH, so if you want to find more about that, you can do that. The high level is that line gives you access to our internal scene information, and so any renderer that you put this into is going to need something to pull the scene information into your ray tracing, and so it's non-standard, but everyone's going to have to do something to pull that information in. And so with that C code and that shader on the right, you get something that renders that thing on the top, and I've put the scene rendered a little bit more interestingly on the bottom just so you know what you're looking at. So you see blue in the window where you don't hit anything and red everywhere else. So most of you probably understood what I just said, but let me run through this in English. So these first couple lines in the ray generation shader take your pixel ID and convert it to a ray through the center of your pixel. This code here takes that direction, creates a ray, and traces that out through the camera into the scene. If you hit something, you execute the hit shader here, and you return red. If you hit nothing, you execute the miss shader here, and you return blue. And then when you're done, when you've either executed a hit or the closest hit shader, you come back here after you finish the trace ray call, and you write that out to your buffer. So that's what's going on. All right, so let's go to a more interesting example. And this is an example in the tutorials you can get online. Let's build a ray traced G-buffer. So for those of you who don't know what a G-buffer is, it's commonly used in deferred rendering. And the basic idea is you're going to save all the visible geometry in a first pass, and then you'll shade it again in some later pass using some more complex shader. And so it might look like something like this, and for those of you who are game developers, you're going to say, wow, you're going to store a full position buffer, but yes. For this tutorial, I'm going to dump out a position, a normal, and a diffuse material. So what might the shader code look like for this? And in this case, I'm going to change a few things up. I'm actually going to write out my color in the closest hit shader rather than in my ray generation shader. So what's going on here? Well, I need to pass in the textures that I'm going to store out. Remember I had 3. I had a position, a normal, and a diffuse texture. So I passed all of those in as rewrite textures, UAVs, and DirectX. And I'm going to output those values there. Here, this is a tutorial-provided utility for accessing our scene information. This gets information about the current hit and your closest hit shader and returns it in the shading data structure. If you think about what do you need to get information to shade, you need to figure out your material, you need to know what triangle you're on, and you need to know where you hit that triangle. So you need to pass in a primitive index and the intersection attributes, which are barycentrics in DXR. So the ray generation shader looks actually almost identical to what I just showed you in the last tutorial, except I don't have an output at the end. Once you return from the trace ray, you just end. And that's because, again, I wrote the output in the closest hit shader. In this case, I'm not actually using the payload. Currently, the payload needs to be a structure, so I define a dummy structure and pass that in along with the ray. And my miss shader, I'm going to assume that you clear your buffer before you run your gbuffer pass, so my miss shader doesn't do anything. And then again, I add this non-standard import ray trace and give you access to the scene acceleration structure and information about the scene to the top. So everything below that is standard HLSL, and that's not. So with that, you get that shader. The shaders give you those output buffers for this scene over here. All right, so now that you have a gbuffer, and you can generate the same gbuffer with raster, and in fact, one of the tutorials shows you how to do this with raster, and one shows how you do it with ray tracing, if you want to compare and contrast. Once you do that, you can do something more interesting with that buffer. Maybe you could do ambient occlusion. So what is ambient occlusion? For those of you who don't know, it approximates the incident light over a hemisphere, and it gives you this sort of very soft shadow, sort of like you see here. This uses 1 ray per pixel. And it's really simple to implement. You shoot a random ray over the hemisphere. You check whether you see any occluders within a certain specified distance, your ambient occlusion radius. And if you don't hit anything, you return 1, it's lit. If you do hit something, you return 0 for black. There's more advanced versions of that, but that's the simple way. So how is this code different than what I just showed you? Well, it runs in 2 passes. It generates a gbuffer and then spawns rays from those hit points to compute ambient occlusion. I just showed you how to do that. So the next step is this part, and we're going to focus on that. So let's look at the ray generation shader for this ambient occlusion. It's a little bit different because I'm not spawning rays from the camera. I'm looking up their origins and the surface normal from a texture. But because I'm doing some randomization, I need to create a pseudo-random number generator. So I'm going to do that using the launch index, the current pixel on the screen, to help seed my random number generator. This is fairly standard. See the code for details. After that, I'm going to load the position from my gbuffer. Remember, this is the texture I output in the prior pass. So this stores the position that I hit some geometry at that pixel. I'm going to load that, and I'm going to load the surface normal as well. Then I'm going to set my default ambient occlusion value. And why do I need to do this? Because, well, if you hit the background like these black pixels here, I need to have some ambient occlusion there. I'm not going to spawn new rays. I'm going to call it 1 for completely lit there. And then at the end, I'm going to output this out into my color buffer once, either directly or once I spawn my ambient occlusion ray. For ambient occlusion rays, I'm going to get a random direction. You can see the code for the details of doing this. This is pretty standard random selection of array on a hemisphere. In this case, it should be cosine weighted, and that's also in the code. And after that, I shoot a ray. Now, this shoot AO ray is a wrapper I've written around ray tracing, and I'll go show you that in a moment. I'm going to shoot the ray from my position that I looked up in the gbuffer in the direction of this random ray. And the min and max distance I'm going to pass in are 1e to the minus 4. This is this fudge factor that Pete talked about in his talk, so you don't do self-intersections. And the maximum value is something that I'm passing down from the seaside, so you can change the radius dynamically of your ambient occlusion. If you want only nearby details, you can use a small value, and if you want whole scene ambient occlusion, you can turn this up to a very large value. So how do we shoot our AO ray? Well, it's actually very simple. And note, this code will be in the same shader file with what was on the last slide. In the shoot AO ray function, I'm going to set up my ray description. That's the origin, min t, direction, and max t. And those are just taken from the parameters to the shoot AO ray function. I'm going to create a payload, trace the ray, and return that payload from this. Now, one thing you might notice is my payload here, which is defined up at the top of the slide, is either going to store 0 or 1. 0 for I hit something, and 1 for I miss something. And I'm initializing it to 0, which means I'm assuming that my ray hits. Then I'm going to define the flags for my trace ray. This is a little different than the rays I've traced so far, in that I'm adding some special flags. This one, the skip closest hit shader, says we don't need to shade. I'm either returning 0 or 1, and I'm assuming I hit, so I've already set the value to what I need if I hit. So I don't need to execute a closest hit shader. And since AO rays are basically visibility rays, as soon as I have any hit, I know I'm done. I don't need to continue searching. Just finding 1 is good enough. And both of these speed my performance, or improve my performance quite a bit. My miss shader, if I don't hit anything, I set this return value to 1. If I hit something, here I'm doing an alpha test. I run a little program, or excuse me, a little function here, alpha test fails, which is specific to my tutorial because it has to query the texture. If I hit a transparent part, I ignore the hit. If I don't hit a transparent part of the texture, I keep going. And that is the code on the DX side for ambient occlusion. So on the C side, just sort of to remind you, I don't have to change very much. Remember our HLSL variables are this. I need a position texture, a normal texture, an output texture, and this ambient occlusion value here. And in the C++ infrastructure that I have, which I think this is the last time I'm going to talk about it, you specify those variables in this way. This here is grabbing the texture for the position. This here is grabbing the texture for the normals from my G buffer. This is my output texture, and here's how I pass a float value into this constant buffer in the shader. All right, so that gives us ambient occlusion values that look something like this on the left. But what if you want more rays? What if you want less noise? Let's shoot some more rays and use, in this case, 64 rather than 1. So to do that, it's actually pretty straightforward. I need to pass in the number of rays that I want to shoot, and I now put a for loop around my shoot ray and accumulate the values from multiple ambient occlusion rays and average them, divide by the number of total rays that I'm shooting. And so it's very straightforward to go from one sample, one AO ray, to multiple ones. The only difference is you have to pass in a new value from your C code. All right, so next I want to add diffuse shadows and global illumination. We've sort of been doing some really simple stuff, a G buffer and ambient occlusion. Let's go to something more interesting. So of course, diffuse lighting looks kind of flat and boring. You can add shadows, which add a little bit more, presence to those bits of geometry. And if you add global illumination, it adds quite a bit. So let's talk about how you add those. So again, how is this code different? Well, it shoots 2 types of rays this time. It shoots a shadow ray, and it shoots an indirect ray. The shadow rays just test visibility, and the indirect rays return a color. So in this case, shadow rays are identical to AO rays that I just talked about in the last set of slides, except I've renamed them to say shadow instead of AO, but otherwise they're identical. There is one slight change, though, to the shadow rays, is because I now have 2 types of rays, the parameters to trace ray need to change. Rather than passing in 0, 1, 0, which is what I did for ambient occlusion, I now have multiple types of hit shaders and miss shaders, so I have to pass in the appropriate values here. So in my tutorials, shadows are hit group 0 and miss shaders 0, and there are now 2 hit groups because I have both a shadow ray and a color ray. So this will be 0, 2, 0 rather than 0, 1, 0 as it was before. So color rays are a bit more complex. And let's talk about how. So first of all, the payload now needs to be a little bit more interesting than just a single float, which is either 0 or 1. And so in this case, I'm going to have a color stashed in there, and I'm also going to have a random seed to allow me to pick a random direction and reuse the seed along all rays in a pixel rather than reinitializing it, which would lead to interesting artifacts. The mist shader needs to return the background color. Here I'm wrapping it in a function get background color that you'll have to define yourself. This could just return blue if you want. The hit shader is actually identical to the hit shader for shadow rays because all I'm using it for is to test whether I've hit a transparent part in my texture for alpha testing. So that's actually the same as my shadow ray, any hit. And in this case, we actually have a closest hit shader unlike the shadow ray. And so what's going on here, again, both of these are shading specific. The first line of the closest hit shader here is querying my scene representation to return this shading hit, or excuse me, the shading data structure. And then the second function is actually shading it with the diffuse shade function, which I'm going to talk about in a moment. So shooting a ray is pretty simple. It's actually simpler than the shoot AO ray because I'm not setting special flags. The only real key thing to note here is that since I now have two ray types again, the parameters for my hit group, total number of hit groups, and mist shader are 1, 2, 1 because that's how I've specified them in the C code. I'm now using the appropriate hit and mist shader for my color rays. So now let's take a look at this function, diffuse shade. What happens here? So in diffuse shade, the first thing I'm going to do is I'm going to pick a random light to do direct lighting from. I'm not going to shoot a shadow ray to every light. I'm just going to shoot it to a random light. And so I pick one of the lights in my scene randomly, and I define what the probability of sampling that light is. I'm going to sample them uniformly, so it's 1 over the number of lights. And you'll see why I get to this in a moment. The next thing I need to do when I'm doing diffuse shading is I have to get information about that light. So in this case, I'm accessing a data structure that's specific to our tutorials, our framework, called G-lights, which stores the information about the light. I'm pulling the intensity and position. I'm going to compute the distance to the light and the direction of the light so I can shoot a shadow ray. Then I'm going to do some shading computations. Again, this is diffuse, so I'm going to use a Lambertian BRDF here. So I need to compute n.l. Well, I need to do that anyways. But there's n.l. I want to make sure it's in the range 0 to 1, so I'll saturate it. And then I'll shoot a shadow ray, which is that function that I defined before. And this will either return 1 or 0, depending on whether you're lit or not. My ray color is then the intensity of the light times that 1 or 0 that I return. It's either bright or it's completely shadowed. And then I return that shaded color from my function. And you might say, oh man, that looks kind of complicated. What's going on there? As for most shading, if you want to figure out how to do shading right, you should really go back to the rendering equation. And I'm going to walk through this very, very briefly so you understand what the heck's going on there. So this is the rendering equation, right? You get your BRDF times your incoming light times this n.l term, and you integrate it over the hemisphere. Now, most of the time, we're not actually going to do analytic intersection or analytic integration. We're going to do something like Monte Carlo sampling, which will look something like this. Now, in our case, we're only shooting one shadow ray here, so n is 1. We have n.l that we just computed above there in the shader. We have our incident light direction, which is the light intensity modulated by our visibility term. And we have the BRDF, which for physically based diffuse is the albedo over pi. And then we need to divide by the probability of our sampling, which is why I computed that up top as 1 over the number of lights. And so that is my diffuse shade function. So our ray generation shader is pretty straightforward. We're going to launch a ray, figure out our random seed. We're going to grab our hit position, our normal, and our diffuse color from our G-buffer textures. We're going to compute our direct shading at the surface using that same diffuse shade function I just defined. So I'm going to use that once here in the ray generation shader and once in the closest hit shader. And then I'm going to shoot my global illumination ray. Again, this is only one bounce. So here what I'm going to do, I'm going to get a random direction to query what's the incident light in this random direction. I'll shoot my color ray, and then I'm going to accumulate it with my diffuse texture color. And then I'll output the result to my output texture. And this accumulation here is deceptively simple, but it's not really. And for those of you who've written ray tracers before, you've probably had to add random values of pi and 3 and e and all sorts of other random things because you're not quite sure what's going on. And so really, whenever you see something deceptively simple like this, you should go back and look at the rendering equation. And so you might say, well, what's going on? And the key thing that you may or may not know is that for cosine weighted samples, the probability is this. And so that allows us to cancel the n dot L, and then our BRDF, we should be using pi times the normal BRDF. And physically based renderers are diffuse over pi, so the pi's cancel. And that's how we get this deceptively simple result. So you should remember this when you're doing ray tracing, and you're not like, what should I do for shading? Go back to the rendering equation. And so we get something that looks like this for a number of different scenes. But that's only one bounce. What if you want to add multiple bounces? So one bounce looks like, well, no bounces looks like this. This is direct lighting only. Adding one bounce improves things quite a bit. Adding 2 bounces gives you even more. And so maybe you want to add multiple bounces to your renderer. So these extra bounces can have a big impact, but it doesn't really have a huge code change with ray tracing. So remember our closest hit shader that looks something like this. You get the shading information from the scene, and then you call this diffuse shade function. We don't have to do much to add multiple bounces. We just add some global illumination stage right here, which looks exactly like it looked in the ray generation shader I just showed you, except for this if statement. And the reason we do that is we don't want to bounce infinitely, or you'll get stuck in an infinite loop and your code will pause and die. You don't want that. You want to limit the number of ray bounces to something reasonable. And in fact, I've passed this in as a parameter so you can control it and add more bounces as you go. This also requires your payload to have a ray depth, and that's provided there. And so you compare your ray depth against your maximum ray depth and don't shoot a GI ray if you've gone too far. So with that, you get something that looks like this. Now, what if you want a different material model? Well, that's pretty straightforward. Remember this diffuse shade. You can pass in you can define a new function, perhaps one that does a GGX model there. I'm not going to walk into that. That's in the tutorials online. And again, you also have to change your global illumination rays here to use a GGX model or whatever model you'd like to use. So you need to change your shading, and that's it. So with that, you might get something that looks like this. And again, all of these images are rendered using the tutorial code that you can download, and most of them are free assets that you can play with as well. One last example, and that's the one I showed as people were filing in, sphere rendering. So all the examples I've used so far have only been standard raster scenes that we've been using in our research team for quite a while, meaning only triangles. But one advantage of ray tracing is you can do arbitrary shapes like spheres. And so just for the purpose of this tutorial, I want to walk through one of those, which is spheres. You can figure out how to do other ones a fairly straightforward way from that. So what do we need to do sphere rendering? Well, we need to define how rays intersect a sphere. And I'm not going to walk through the math of this. There's plenty of documentation online. You can Google ray sphere intersection and find pretty good resources. But what you need to do is you need to write an intersection shader. In this case, I'm calling it sphere intersect. And in order to do this, you need to know information about your sphere. So the first thing I do in my sphere intersect is I ask the question, what sphere did I hit? Pull the information from some buffer about my sphere. In this case, my G-sphere data is an array of spheres in my scene that stores x, y, z being the center of the sphere, and the alpha component, the W component, is the sphere radius. So I just put those into a couple of variables there. Then I do the math for ray sphere intersection. Again, I'm using the intrinsics world ray direction and world ray origin as part of this computation. This is a quadratic equation. You get A, B, and C. You plug it into the quadratic equation, and you may not hit. You may get an imaginary number, in which case you can just return. You didn't hit anything. But if you have a real solution, you call report hit. You say, aha, I found a hit. And in the case of the sphere, you actually have 2 hits, one in the front and one in the back. And so you define sphere attributes and call report hit with the distance to your hit, the user-definable hit type. In this case, I'm not defining anything interesting. I just passed 0. And then the sphere attributes. In this case, my sphere attributes are really dumb. I'm just passing through the center of the sphere. I don't claim that's a good idea. In fact, it's probably a bad idea. But that's what I'm passing through here. And then for shading, it's also pretty simple. I get the information about the material of this sphere. I compute the normal, and I do this by finding the hit point on the sphere, minus the center, which is why I pass that to the attributes and normalize that. And then I shade with one of a couple of different functions, either a diffuse material function, metal material function, or glass material function. I'm not going to walk through these. These are in the tutorial code. And that gets you this, which is Pete's ray tracing in 1 weekend final image with a few added bonuses. All right. To summarize, I've presented an overview of DirectX Raytracing shaders. There are 5 new shader stages you need to pay attention to. There's the ray generation shader, the intersection shader, miss shader, closest hit shader, and any hit shaders. And I tried to walk through the new built-in HLSL functions for ray tracing at sort of a fast speed. We walked through a number of samples demonstrating their use. For full code, additional tutorials, and runnable executables, you can go online to the course webpage and download all this code for yourself. So what I hope you've taken away from this morning is the shader side of DirectX ray tracing looks very, very similar to coding a serial ray tracer in CPU, on the CPU. And it's actually pretty straightforward to get started if you have some encapsulation of the host side code. I hope you go out and try it. You grab my code, you play with it, and this code hopefully hides the ugly stuff from you, so you can play just with experimental prototypes for those of you who are researchers and may know nothing about DirectX. All right, so I think with that, I have time for a few questions, and we're on time for a break, after which we'll come back at 10:40, and Sean will talk. I'm happy to take questions during the break. Otherwise, get up and take a stretch.
So just a few questions. I just wanted to make sure. As far as your G buffer is concerned, the positions and the normals were in world space as opposed to camera space?
Yeah, they're in world space.
Okay, on the ambient occlusion, did you incorporate ambient inclusion in that final sample of yours?
No, no,
Okay.
I don't.
So the distance you were specifying for the hemispherical integration was arbitrary. You were just a fixed constant.
Yep.
Okay, and then finally, like when you showed those multiple bounces, were you attenuating the light based on the distance squared?
No,
Is there a reason why you weren't?
because you don't want to.
Yeah, because obviously the dark scenes look darker, and like the light doesn't propagate all the way across. Or
yeah, the math of the rendering equation that handles that for you.
oh, okay, all right, thank you.
Yeah. Hey, hang on.
Oh, I see.
Okay, go.
All good? Perfect. So your ray generation shader actually seemed maybe deceptively so similar to our standard compute shaders we have today. Is there any reason why the choice wasn't made to extend our existing compute shader architecture to support ray generation? And to follow up on that, it seems like the ray generation shaders have the capability to dispatch other shader stages. Is that something we might see in the future in existing rasterization or compute shader stages?
Well, So I can't really talk to the design because I wasn't involved in the design of this API. So you'll have to ask that to maybe Sean can answer that. So on the launching, I mean, part of the reason there is this callable shader type is because I think people realize that people look at this API and realize you could launch new shaders, and let's explicitly call that out as a callable shader type to make that clear. I didn't talk about that here, but if you want to call shaders, you can do that.
Awesome. Thank you.
Let's go in the middle there.
Hi. I want to know if the payload structure needed to be the same across all shader stages, or can it be custom per stage so you optimize the VGPR uses?
It needs to be the same across array. So throughout the ray type, you need to use the same shader payload. Different ray types can use different payload types. And
So
in the tutorial, the shadows and the color both had different types.
Okay, so it's per array, so you cannot optimize that part so
No,
you get the cost across.
the any hit shader and the closest hit shader need the same payload.
And then I was also wondering about the geometry mask. Is there any difference between using geometry mask versus kind of moving that into the payload and then do that in your it shader directly?
Well, so doing it with like the instance mask allows presumably allows the driver to do some optimization behind your back rather than doing it programmatically. I'm not entirely sure how that works.
Thank you.
Do current GPU debugger tools work, or should we expect to receive updates or new tools for the ray tracing API?
I haven't used them extensively, but other folks on my team have used a lot of the same developer tools, and as far as I know, they're working pretty well, but I don't know much about, if they're available now or when.
Okay, thank you.
Similar question to the compute shader one. If I currently have a compute shader that I'd like to do ray tracing from, but only sometimes, would I just move it to a ray generation shader and then sometimes trace array, sometimes not?
Yep,
Okay.
you could do that.
Great, thank you.
I was actually wondering, you seem to have a lot of if branching, and with multiple shaders, multiple hit groups and whatnot, it all sounds like it's very, offensive to shader locality. So it's more of an architectural question, but are we still concerned about waveform performance and shader locality and that sort of thing?
So I don't want to talk too much about architectural details. You still have to worry somewhat about coherency, and I think at this point I'm not sure I know enough about performance characteristics to actually answer you.
Yeah, that's okay. Thank you.
Let's go over here.
Hi. Hey. So you kind of abstracted away a lot of the details of getting material properties. Pixel shaders make it really easy to do things like bitmap selection. What's the general guideline for that here?
Well, it's an excellent question. There is no quads like there is in raster, so you don't have derivatives automatically. You can either do this explicitly with ray differentials, which are pretty heavyweight. There's an approximation that I believe Thomas Akin-Muller is publishing in Ray Tracing Gems, and that chapter I think is online. They announced at HPG. I don't have the link handy, but that's sort of an approximation that you can use instead of ray differentials. And there's probably more work that needs to be done here to say, how do we do this quickly in maybe an approximate way that this is faster than ray differentials, which does add a fair amount of overhead.
Thank you.
There is any concept of LOD in this pipeline. So I hit an object very far away and I want to switch from a very detailed object to a few.
So as far as I know, there's no built-in concept of LOD. You're going to have to do that yourself.
there is any way to implement it? Just switching accelerated structure when I hit a box or something?
You can use multiple acceleration structures. I have not done this, so I can't provide you much more detail on this.
Thank you.
Yeah, you should probably ask maybe Sean or Colin, who may have more experience with this.
Hey, so I want to know how you guys provide the scene geometry to the ray tracing API, because there's no part of the code that send all the geometry so the API can build the BVH, so the ray trace can trace the intersection geometry. Is it like implicitly you need to set, or is it explicitly?
Well, so in these tutorials, it's all extremely abstracted. I haven't done a lot of profiling directly. You're probably better off asking one of the guys who's done that sort of work.
Okay, thank you.
Hi. In your tutorial code, you showed this function nextRand.
Yeah.
And so I wonder if random number generation is something that is built in, or is it something I have to care?
No, the random number generation are utilities provided in my code. It's not a very good random number generator, it's just one I picked. You're probably better off using not random numbers, but something else. Yeah. And mine were all uniform random entirely. You probably want to jitter if you do use random numbers. This is just get you started. Use something else probably for real.
Thank you.
I have a question about the noising.
Yeah.
Is it possible to expose the tensor core denoising to DXR? Is there any plans?
Well, I can't speak to plans. Yeah, I don't think I can answer that right now.
Okay, thank you.
All right. Yeah. Hopefully I didn't murder things too bad. Oh, thank you. All right, for those of you at the back, stop talking. Let's sit down again after the break and get started. So next up in the course is Sean Hargreaves from Microsoft, who's going to give an overview of the host side, the API code, Introduction to DirectX Raytracing, the API.
Good morning. So I'm Sean Hargreaves. I work at Microsoft on the Direct3D team. And at this point, you're hopefully all interested to start using ray tracing and convinced that there's interesting things to be had here, interesting research to be done. I'm going to start talking about the next step beyond when you're ready to apply ray tracing outside of a sample framework, just working on the shaders. If you want to integrate this into an existing game engine, or write your own framework, what does the API look like that you need to write to do this with? The other way to put this section of the talk is going to be talking about the ugly stuff that we've skirted over so far. And there's some ugly stuff, I should forewarn you. So there's basically three things that you need to do on the host side using the DirectX API. You need to build geometry into acceleration structures that can be ray traced against. Then you need to configure a pipeline state that defines all of the shaders that are going to be used for ray tracing. And then finally, you call dispatch rays. So I'm going to spend the next hour walking through each of these steps. Before I start doing that, though, I need to back up a little bit and talk about D3D12 itself. Can I get a quick show of hands? Who here has written DirectX 12 code previously? Okay, great. That's about what I thought. So some of you have. Apologies to everyone who put their hand up here. I'm going to zoom through DirectX 12 in about 10 minutes. And you're going to be thinking, I skipped over so much essential stuff. How could I possibly simplify to this ridiculous extent? I can't teach you DirectX 12 in 10 minutes, but I can hopefully give enough concepts for those of you who didn't put your hands up that you can then follow what applies to ray tracing. The reason I need to do this is that ray tracing is part of Direct3D. It's not just a separate API off to the side. And we built it that way for the specific reason that we think mixing rasterization and ray tracing is very interesting and important. We expect there are going to be a lot of valuable hybrid techniques, like perhaps you rasterize to build up a G-buffer in a deferred shader, but then ray trace to do reflections or shadows. So having all of this stuff inside a single model where there's one way of scheduling work, one way of describing resources and managing memory is really important for letting you mix and match. But that does mean that step one in getting to ray tracing is you've got to get to Direct3D itself first. So the really kind of high level of Direct3D12, it is a low-level API. And that means that as an application developer using it, you are in control of memory, of lifespans of objects, and of synchronization between CPU and GPU. And these are things that you didn't generally have to worry about with earlier graphics APIs like Direct3D11 or OpenGL. So the general pattern of any programming with D3D12, you start by creating some resources in memory on the GPU. That will be texture maps, vertices, constant data. You put data into these resources. Then you record a set of instructions that the GPU is going to execute into an entity called a command list. And the sequence of API calls for doing that starts by resetting a command list. You configure some state on it. Here I listed the set root signature API. There are many more, lots of state to configure. Then you issue calls instructing the GPU to do work. Typically, historically, that would be draw instance to draw triangles, or dispatch to dispatch a compute shader. With ray tracing, we add dispatch rays to that set. And you record any number of different operations into a command list. You can change some state, draw some things, change some more state, dispatch some rays, change state again, dispatch some compute work. But so far, none of this is actually executed. You're just recording instructions that the GPU is going to do later. This is all just running on the CPU. When you're done building a command list, you submit it to a command queue by calling execute command lists. And this actually kicks the GPU off to go and start processing those instructions. And then finally, you have to synchronize on the CPU side to know when that GPU work is finished. And this is really important because these processes are parallel. They run completely asynchronously. So you can't go and change any data that you've told the GPU to use until it's finished using it. You're going to have all kinds of race conditions if you don't get synchronization right. And as a developer, it's your responsibility to do this stuff correctly. That's done through the Signal API and the fence object. So I'm going to walk through an example of how this parallel model works with something simple but concrete that every application is going to do, like creating a resource and putting some data into it. So you have two timelines here with time progressing downwards down the display. CPU on the left, GPU over on the right. We'll start by creating a buffer in GPU memory that we want to put some data into. Then we have to create another buffer, which is called an upload heap. And the reason for this is that the CPU can't write directly into GPU memory. It can write straight to the upload heap because that's in CPU accessible memory, so we can just scribble some bits into it. We could generate them, we could load them from the file system. Then we issue a copy resource call, which will tell the GPU to copy from that upload heap into the real GPU memory buffer that we want to use. This is still just on the CPU timeline. We've recorded that call, but we haven't run it yet. And now we call execute command lists. This is what kicks off the GPU to actually start processing. So it goes over and communicates to the other processor and starts running some work. And now the GPU goes and starts actually processing that copy resource, which might take a while if the resource is big. Meanwhile, on the CPU, we'd like to know when that has finished. So we call signal on our command queue, which is issuing an instruction to let us know when it gets to that point in execution. And then we can go to our fence object and say set event on completion, which will give us back a Win32 event handle. And then we can call wait for single object, which will block on that event, waiting for it to be signaled. And now the CPU is just waiting because the GPU is still processing the copy resource, so that event has not been signaled. When the GPU gets done with its copy resource, it reaches the signal call and goes and signals that event handle back to the CPU to indicate that it's finished. That unblocks the wait for single object call, so CPU execution resumes. And now we can destroy the upload heap because we know the GPU is finished with it. It's safe to delete that object. Now our data is in the actual buffer that we wanted to use in GPU memory. This is a greatly simplified example compared to what you would see in a large complex game engine where there's probably many, many different fences and signals flying around, synchronizing all kinds of different things. But this is the kind of model you need to have in your head when you think about D3D12, that there are two timelines, and you have to be very aware. You're submitting work from one to the other, and then you have to track when that work is finished. The other big piece of D3D12 to cover is how we bind resources to the pipeline. The sample framework that you saw earlier handles this all for you. But there are some interesting options about how you make textures and constants available for a shader to process. And there are some basically multiple levels of indirection here. We start with a thing called a descriptor. This is a term you'll come across a lot in direct 3D programming. Conceptually, this is a pointer to a resource on the GPU. It's a little bit more than a pointer in some cases. A descriptor to a texture also contains information about the size and format of the texture. So it's kind of like a rich tagged pointer. But conceptually, this is a pointer. Then we have a thing called a descriptor table, which is just an array of descriptors which you can index into. So you could have a set of different textures that we use for animation or for different parts of an object, and then you could use an index to go and pick which one was used out of that table. The third entity we have is a thing called a descriptor heap, which is an area of GPU memory. And in that descriptor heap, there will be multiple descriptor tables at different offsets. It's entirely up to you how you want to manage this. You know, some engines will just create one giant descriptor heap, use the whole thing as one huge table, put all their descriptors into it, and then just index to select them. Others will put many smaller descriptor tables at different offsets within the descriptor heap and can update these and point different shaders to different pieces of the heap. The final object that's involved in resource binding is a thing called a root signature. And this is basically a convention. When you're writing a shader, you will say, okay, this has a texture as an input and a constant buffer, and you give those names. And then in the HLSL code, you refer to these objects by name. The root signature maps how those names from HLSL get back to the CPU side and where the GPU actually goes and finds that data from. So there are three types of thing you can put in a root descriptor. You can inline some constants directly into it. So basically, any 32-bit value can just go straight into the root descriptor, you know, an integer or a float. There's relatively limited space for these, so you don't want to put too many values straight into the root signature, but it's efficient to update them if they go there. You can also put a small number of descriptors directly into the root signature. So something like a constant buffer that you change very frequently from one operation to the next, you might want to just put the pointer to it straight there. More commonly, though, the root signature will contain pointers to descriptor tables. So the binding model there is that the root signature indicates how to go find the table, and then within the shader, you index into that table to find the actual descriptor that you're going to go fetch some data from. So that was a whistle-stop tour of D3D12. Hopefully you've all mastered it, or at least know the right search terms to go look up in the documentation later. So when we add ray tracing, a couple of new things get added to this picture. New complexities introduced by ray tracing come from the format of geometry. Ray tracing traces against acceleration structures, not just vertex buffers. These need to be highly optimized. And there isn't a single canonical format for these because the traversal often will happen in hardware or will need to be tuned in some way to fit the hardware. So unlike vertex data, where we've agreed many, many years ago what an index buffer is, and all GPUs agree, there's no disagreement, it's a set of integers. A vertex buffer is just a set of values. So you can go and just put data into memory in the format that the GPU will rasterize from directly. For ray tracing, that's not the case. The layout needs to be different for every implementation. The second new thing with ray tracing is that rays can go anywhere. The more levels of indirection you use, the more extreme this gets. But even in a very simple case, any ray could hit any object. And that means that all the geometry and all the shaders need to be accessible at the same time. We no longer live in a world where in rasterization you would say, okay, set this shader, draw some triangles, it's just this one object. Change everything, set some different shaders, draw another object. All of the geometry and all of the shaders have to be accessible the very moment you call dispatch rays. And the third thing that comes from that is that different shaders might want different resource bindings. It's very, very unlikely that every single shader you use in a complex scene is going to have the same set of textures and the same constants. And would be excessively limiting for programming model if you had to come up with a single kind of unified set of all of the parameters that might be needed for any shader everywhere, and then go update all of your shaders every time you added a new one with a second parameter. So all of this basically means we need more indirection. We need the ability to select shaders with very fine granularity within ray tracing, and we need the ability to go find different sets of parameters and different binding conventions depending on which shader got selected to be executed. So let's talk about what you actually do once all of these pieces are in place. Step one, we need to build acceleration structures, which is the geometry that we ray trace against. An acceleration structure is an opaque format. It's an area of memory that is defined by the implementation. It's highly optimized for ray traversal. Typically, this is going to be some kind of bounding volume hierarchy, but the design of direct 3D ray tracing doesn't require that. An implementation could innovate and come up with different types of acceleration structure. These are built at runtime on the GPU. They have to be, because depending on what GPU you're running on, it might want a different format. And they're more or less immutable. I'll talk later about some options for animating them. But conceptually, you should generally think about them as being immutable. The model is that you come in with a set of triangles or other geometry, and you hand it to the driver, and it does some work and builds a BVH. And then you can just ray trace many times against that BVH, but you're not typically going back and changing its contents. And this is kind of different to rasterization, where you can change geometry very, very late in the pipeline. Because in the geometry world, you're just kind of throwing triangles at things one at a time. The vertex shader can come in and move a triangle somewhere else, and that's how you do animation. In ray tracing, that's a really different world. You can't late move things when you need to have optimized a structure that depends on the position of everything. So if you want to change the geometry, that means building a new, different BVH that will be optimized a different way. There are two types of acceleration structure, top level and bottom level. So a bottom level acceleration structure is the entity that holds most of the geometry. Typically, these will contain triangles. They can also contain procedural primitives, which are defined by an axis-aligned bounding box plus a custom intersection shader. And that's how you would do it. You saw a demo of using this to do spheres earlier. This is also where you would do curved surface intersection, or if you want to do NURBS or Beziers, or any kind of creative non-triangular structure. Bottom level structures can take some time to build because they contain a lot of triangles. Building the BVH involves work. Then we also have a concept called a top-level acceleration structure, which is basically just a set of pointers to some number of bottom-level acceleration structures plus a transform. So the way you would do instancing, you would have one top-level structure that had multiple references to the same bottom-level structure with a different transform for each instance. You could also just group a set of objects into one top-level structure. Top-level structures are much faster to build than bottom-level structures because they don't contain large amounts of geometry. They're just kind of aggregating bottom-level things that have already been built. So rebuilding these is going to be significantly faster. And so there's a balance to be figured out here when you're deciding how to structure the geometry for a scene. If you want to optimize for raw ray intersection performance, you should prefer fewer, larger bottom-level structures, which will allow the implementation to create very efficient BVHs. If you want more flexibility, you should probably lean towards a smaller number of smaller bottom-level structures, and then more references from the top-level structure, because then you can just move those around and change the top-level structure. So when you come to build these acceleration structures, we need to talk about memory management. The complexity here is that because the format is implementation defined, you don't know how big one of these things is going to be until after you build it. The build does a lot of optimization, and depending on what kind of tree it settles on, it might need more space or less space, or might be able to merge some things. So that's obviously a challenge. How do we allocate memory for something when we don't know how big it's going to be? And the way we do this, we call this API Get Raytracing Acceleration Structure Pre-Build Info. That's a cautious estimate. It runs on the CPU, and it's conservative. So it will return the maximum size that an acceleration structure with the number of triangles or objects in it that you specify could ever be, kind of worst case. That's how much room you need to allocate to build it. Once you've allocated that much space, you call build raytracing acceleration structure. And that actually does the work of doing the BVH optimization. This runs on the GPU. And when it's done, it can return the actual size of how big the thing for real turned out to be. That's going to be available in GPU memory. And it's not available until after the build command has finished executing. There's actually two different sizes that come out of this. There's the current size, which is how big the structure really is today. And then there's a compacted size. Compaction is an operation that can shrink a bounding volume hierarchy after it's been built. So after the build, you can get an estimate of if you did compaction, how much smaller would it get? When you build an acceleration structure, there's a few flags you can specify to control how the build operates. The first couple are kind of performance hints. You can indicate that you would prefer it to optimize for fast tracing at the cost of spending longer building, or you would prefer a fast build at the cost of perhaps slower tracing. And this is really a trade-off of how many times you expect to ray trace against this structure. If you're building it just once at load time, and then you're going to reuse it many, many times on different frames, you should probably go for fast tracing. If this is an animating object that you're going to ray trace against just once and then throw it away and build another version the next frame, you probably optimize for a fast build. You can also indicate that you'd like to spend a little bit of extra build time to minimize memory usage. You can specify a flag to say that you would like to allow compaction, which means that you do plan to later use the compact functionality, and you'd like the build to preserve some data necessary to do that. If you plan on animating this acceleration structure, you have to specify that by saying that you do want to allow updates. And then the perform update flag is the kind of special case. This is how you do animation. You do a second build of the same acceleration structure pointing to the same destination location with the perform update flag. And that means just make some incremental changes to what was already built. So if we want to be efficient about memory usage, we should think about compaction. And this can really matter. Your geometry can be, for a complex scene, we could easily be talking hundreds of megabytes of geometry data. So wasting space here is a big deal. The basic idea behind compaction is to suballocate multiple acceleration structures out of larger buffers. When we're initially building them, we use the conservative sizes. Then after the builds have finished, once we have real size data, we do some kind of compaction pass to shrink our memory usage down. A caution here, don't compact things if they animate, because in that case, even if the current size is smaller, as you animate it, it might need more space. And be aware of stalls. This is important because the builds execute on the GPU. What you don't want to do is submit a build, then kind of immediately block the CPU, waiting for that to finish to find out how big the thing is going to end up being, and now the CPU is just waiting around. For efficiency, you want to find a way to get this stuff all running in parallel. The simplest allocation approach is just not to bother with compaction. You call the get pre-build info, allocate the maximum size that that said you need, call build, and you're done. That's pretty straightforward. But you're going to waste the difference between the result data max size that was estimated versus the actual compacted size after the build finished. If you're okay with wasting that space, totally fine. It's reasonable to do this. If you want to do better, there's a couple of approaches you should talk about. In-place compaction can be done fairly straightforwardly. The idea here is to have one larger buffer with an offset. And for every acceleration structure we want to build, we build to the current offset within that buffer, wait for that build to finish. Now that it's finished, we know the size, and we can just add the current size to the offset and then move on to the next one. This is still going to waste some space. It'll waste the difference between the current size and the compacted size, but it's not going to waste as much space as if we did no compaction at all. The big issue here is stalls. Because we have to wait for the build to finish executing to know how much to offset by, we're likely to end up with the CPU just blocked a lot. A better solution is to do this in 2 passes with a full compaction implementation. So the idea here is we loop over all of our acceleration structures that we want to build them into a temporary buffer with a temporary offset that temporary value by the conservative size estimate. Now we can kick off all of those acceleration structure builds in one go, wait for that to finish executing. We could actually go and start submitting rendering work while this is happening and come back and do the compaction later, like maybe on a subsequent frame after all of our builds are complete. Then once all the builds have finished and we have real size estimates, we do a second pass, loop over all the acceleration structures, and call copy ray tracing acceleration structure from the temporary buffer location into a real buffer, specifying the flag that we want to compact it. And then we can offset into our real buffer by the compacted size, which we know because we already did the build. This approach is going to not waste any space at all. And you can imagine this could be made more flexible. You could do more dynamic allocation if you have things that are animating. So this is a good kind of starting point to think about how to manage memory for geometry in ray tracing. We should talk about animation. Ray tracing static scenes is all well and good, but if we want to do something interesting, we probably want it to move. And the way you're used to thinking about animation in rasterizing doesn't translate directly across to ray tracing. So for rigid body animation, the basic idea is we just update the top level structures. We've already built bottom level structures, we leave those alone. Build new top level structures with different transform matrices, or we could add or remove references to bottom level structures as objects join or leave the scene. This is very straightforward. If we want to do skinning, though, we need to do a full bottom level rebuild because we want to move actual vertex positions. So the basic idea for skinning is to do one pass that transforms vertices into a temporary buffer using a compute shader to do the same kind of calculation you would do in a vertex shader for skinning if you were doing rasterization. And then we take that new set of transformed positions and apply them as an incremental update to an existing bottom level acceleration structure. When we do an update, that's much faster than doing a full bounding volume rebuild because we don't do typically the full optimization passes. What will happen there is we'll just go and overwrite the positions of all the triangles with a new set of positions and then refit the bounding boxes as things have moved. We'll just grow and shrink to match. The challenge with that is that the more things have moved, the less good the BVH that comes out will be because that BVH was built for the original geometry, not the modified geometry. And if we just go and update bounding boxes while still using the previous BVH, we could get a pretty inefficient tree. So the thing here is the more things have moved, the less efficient this is going to be. What you might want to do is do incremental updates for some period of time, and then if your geometry has deformed so far, you have some kind of threshold and periodically go and do a full tree rebuild. A lot of times this is fine though. For character animation, what you should typically think of doing is build your BVH with the character in a typical rest pose. And then you can just do incremental updates forever and it'll be fine. If they move their arm up, the triangles in that arm are not going to fit the BVH as well until they move it back down again, and now you have more efficient ray tracing. But on balance, that's probably good enough. Obvious kind of caveat to that, that's only true if you do your skinning in object space. If I build my BVH for a character in rest pose and then translate them around the world and rebuild new vertex positions where they're a mile away and facing in the opposite direction, that BVH is not going to be a great fit anymore. Don't skin in world space if you want to do incremental BVH rebuilds. A few other options that come into play as we're rebuilding acceleration structures. There's a feature called instance masking. The way this works is that every entry in the top-level acceleration structure has an 8-bit mask, which you specify. And every time you call trace ray, you get to pass an 8-bit mask. During the ray traversal, these two masks get ANDed together. And that section of the geometry will only be considered for hits if at least one bit is set in that result. So this lets you include or exclude pieces of geometry very easily without building entirely separate acceleration structures. This is a great way to do things like flag specific objects to say, I want this to participate in my diffuse rendering, but not to cast shadows. And just have a bit that is this object a shadow caster? And then when you cast your shadow rays, you can just set that bit and off it goes. This is potentially also useful for things like LOD. You could have high and low detail versions of objects that are selected depending on which type of rays are being cast. So you could have a fully detailed version for the primary rays, and then secondary and diffuse rays could use lower detail versions of objects. So a lot of potential to come up with interesting uses for these flags to avoid things that would otherwise require rebuilding acceleration structures or having multiple acceleration structures. So great, now we have geometry, and we're ready to configure some pipeline state. This is the second big piece of setting up ray tracing. And the concept that you need to understand here is a thing called a shader table. The reason we have shader tables for ray tracing, whereas in rasterization in DirectX, we have just one pipeline state active at a time, and you change it by calling set pipeline state. That doesn't work in ray tracing because rays could go anywhere. They could hit everything, anything. If we have a complex scene, we want different objects in the scene to have different materials on them. And that means that we need to run different shaders depending on which object a ray hit. If we didn't have this feature, you would have to write a single giant shader that contained a huge switch statement saying, what did I hit, with cases for every possible material. That's not a very entertaining programming model, so we chose not to inflict that upon you. And instead, we built support for shader indexing into DirectX Raytracing. So the basic idea is that we set up an array of pointers to shaders, which is called a shader table. And then every time we need to run a shader as part of the ray tracing pass, we index into that array, determine based on which object was hit, pick the shader that corresponds to that object, and go execute it. It's effectively an array of function pointers on the GPU. So what does that look like in detail? I'm going to introduce some new terminology here. So we start with a concept called a shader identifier. A shader identifier is basically a pointer to a shader. It's actually 32 bytes, which if you're used to pointers, you'll think is probably rather fat. Obviously, it contains more information than just a pointer, but conceptually, this is a pointer. The next concept we have is a thing called a hit group. And a hit group is a triad of shaders. It combines an intersection shader, if you're using one, the any hit shader, and the closest hit shader. And these are all optional, so typically you'll have a lot of objects that have a closest hit shader, but maybe not an intersection shader or an any hit shader. You could have all three if you need to use them. You gather these things up, combine them to form a hit group, and then that hit group is itself treated as a shader. So the hit group itself has a shader identifier that points to it. And we can say, okay, that hit group is used to shade this object. The reason those three shaders are grouped is because they're the shaders that depend on which object was hit. Miss shaders obviously don't depend on the object that was hit because by definition, if the miss shader is running, it's because nothing got hit. So they're not part of the hit group. The next concept we introduce is a thing called a shader record. So a shader record is an area of memory laid out with a shader identifier, indicating which shader to run, and then a set of root arguments. And these are the exact same things I talked about earlier that go into a root descriptor when you're programming with rasterization. So this can be immediate constant values. root descriptors that point to resources, and shader tables, which refer to indexable arrays of descriptors. So we'll gather up all the parameters that this shader is going to need to execute and just put them in memory right after the pointer to the shader. So a shader record tells us what code to run and what parameters to pass to that code. And then finally, we have a shader table, which is just an array of shader records, however many of them, however many shaders you would like to use for this ray tracing scene. Just put those one after each other in memory. There's not actually any dedicated API for creating shader tables. It's just memory with a canonical, well-defined layout. You can create this however you like. You might create it on the CPU and go copy some data into a buffer. You could also actually create these on the GPU. So it's entirely possible to have a compute shader pass that runs early in a frame, generates a shader table, puts a load of parameters wherever you need them, and then later you can go and do ray tracing using that shader table. Let's look at an example, because I probably confused it with that number of levels of indirection. So this is an example memory layout of a very, very simple shader table. This one has 3 shader records. Each record starts with a shader identifier, which is a hit group. And then it has a set of root arguments. And you can see that the root arguments are completely different for every shader in my table. I start with a shader that I'm going to use for my terrain. So that has no intersection shader, no any hit shader, just a closest hit shader. And it takes a couple of descriptor handles. One of them contains some terrain textures. The other one contains some light maps. I don't know why we're using light maps when we have ray tracing, but hey, we haven't quite got to the full integration yet. We're not doing indirect light bounces. Then we have a root descriptor that points to a constant buffer that's going to provide some parameters for the materials. And for some reason, we put the fog distance just directly in the root signature layout. That's just to demonstrate you can put immediate float values as well as descriptors that point to other resources. We also have a water shader, which is using any hit and closest hit. And it has a couple of different parameters. And then we have some kind of volumetric cloud intersection thing, which is using a custom intersection shader. And that has a couple of root descriptors pointing to some parameters in a constant buffer and to a volume texture. So these layouts are totally up to you. It depends on which shaders you write, what parameters they want to take in. You just go put those in memory after the pointer to the shader. It's important to note that I then have to go and pad each of these rows in the table. The reason for this is that this is a fixed size table. The stride is up to you, but the stride has to be constant for all of the entries. So the size is determined by whichever of my shaders needs the most parameters. You just have to go and pad all of the other records so that they're all the same size. And then it also has to be 32 byte aligned. So in this case, my largest set of root arguments is the first shader. I added 4 bytes of padding to round that up to 32 bytes. Then I had to put 20 bytes of padding after my second and 16 bytes of padding after the third. And that creates me a nice little shader table, which I can point the ray tracing pipeline at. So now I've got a set of arrays arranged into a table. How do I control which one actually gets executed when I call dispatch rays? Because so far it's just some pointers to things. There's a fairly large number of arguments and options that go into this. When I call dispatch rays, I provide 3 tables, and for each of these tables, I just provide a pointer to the start of the table and the stride value, which is determined by how many root arguments I had, so how big my records are going to be. I have one table for all my miss shaders, if there are multiple. I have another table for my hit groups, and I have a third table for my callable shaders. We're kind of skipping over callable shaders today, but they follow very much the same pattern as everything else. So that's right at the start of ray tracing. I provide my tables. Then when I call trace ray, I get a couple more parameters. I can specify a ray contribution to the hit group index. I can provide probably the longest named parameter that exists anywhere in DirectX, multiplier for geometry contribution to hit group index. That's probably not even obvious from the name of it what it does, but my next slide will clarify. And we also have a miss shader index. So that's every time I trace a ray, I get to specify those 3 values. We also have a source of data coming from the acceleration structure itself. So the top level acceleration structure For every single instance within that structure, it provides an instance contribution to hit group index. So how do these things work together? Well, I'm going to start with miss shaders because they're by far the simplest. When we miss and we want to decide which shader to run, we find the address for the miss shader by taking the start and stride that were specified when I called dispatch rays, multiplying the stride by the index, which was passed when I called trace ray, and that's the one we use. It's pretty straightforward. The way to think about that is when you call trace ray, you just specify the index to which miss shader you want to use, and that index is just looked up into the miss shader table. There's no other contributions to that, and there doesn't need to be because there's only one kind of miss, right? The reason you would specify different miss shaders is maybe the misbehavior for your shadow rays is different to the misbehavior from your primary rays or your indirect rays. So at the point when you trace, you know which shader you want to run out of the different options. Hit group indexing is a little bit more interesting because when we hit something, we are going to want to shade it. And the way we shade it is going to be different depending on what it was that we hit. So the selection of which hit shader to run is a combination of the ray contribution, which was a parameter to trace ray, the geometry multiplier times the geometry contribution. And what's happening here, the geometry multiplier was a parameter to trace ray. The geometry contribution is just an index into the bottom level acceleration structure. It's a system generated value for every mesh within that structure that goes 0, 1, 2, monotonically increasing. And then we also add in the instance contribution, which came from the instance in the top level structure. That's kind of a complicated formula. It's getting to the point where it almost seems like, why don't we just make that be something that your shader itself could just do in code? The reason that's kind of obvious we can't is because this is the calculation that chooses which shader to run, so we don't have any code running until we've chosen which code to run. So this has to be more of a kind of fixed thing. A lot of the time, some of these terms will collapse to 0. So the kind of very simple use that you'll see a lot is that you have your ray contribution be 0, and your instance contribution be 0, and your geometry multiplier be 1. And that just means use the index of the geometry to pick which shader into the table. And then you just put entries in your shader table, matching the layout of the meshes in your structure, and off you go. You could also, if you have kind of different meshes that you want different offsets, you might have a set of shaders that are indexed by the geometry at one offset, and you use that for all your primary rays. But maybe for shadow rays, you just don't care and you don't want to run a specific thing. So for shadow rays, you would set geometry multiplier to 0, which means ignore which geometry got hit, and just have the ray contribution say, oh, this is the index for the shadow shader that I want to go run. So there's quite a lot of flexibility in this equation by choosing different values for the coefficients. But this is a crucially important thing to understand. And this is something that we expect there to be interesting innovation in as people come up with the most efficient way of managing shader tables. You have this choice of what shaders do you put at what indexes within the table, and then how do you configure this equation to pick which one of them gets run. And you can use that in a whole bunch of different ways. Okay, so now we've set up our shaders. The piece I skipped over when I was talking about populating these shader tables is every shader record starts with a shader descriptor. That's a 32-byte blob. Where does it come from? So we should talk about that. The general model for compiling shaders, you start with HLSL shader code, which you write awesome algorithms and make it really cool. Then you feed that stuff into the shader compiler, dxc.exe. That gives you back a thing called a Dixel library. This is a bit different to when you're compiling shaders for rasterization, because typically you will just compile them all the way down in that world and produce a compiled vertex shader or pixel shader that you can pass straight into Direct3D. For ray tracing, because we have this requirement that all the shaders are available up front, they all need to be given to the implementation at the same time when you're initializing. And that means there's a little bit more management involved to do this efficiently. You might want to do things like give the driver the option to compile sets of shaders on different threads, and there's configurability over how this works. So at offline compilation, we basically only produce a library which contains a large number, whatever number is right for your application, but all of the different fragments of HLSL code. They're not yet linked together into a single thing that can run on the hardware. So then at runtime, you load in that compiled Dixel library. You create sub-objects and set associations between them, which is how you describe which pieces of code map to which parts of the ray tracing pipeline. Once you've configured everything, you call create state object to create a state object type ray tracing pipeline. And that is the complete set of shaders that you're going to use for a trace ray. When you call trace ray, you configure, just give it that state object as the thing to use. And then after you've done that, you can look up shader identifiers. You can ask that state object, give me the shader identifier for my generate rays shader or my cloud intersection shader. And it will give you back a 32-byte blob for each of those shaders that you ask for. And then that's what you go and put in your shader records to populate your shader tables. I'm going to walk through this with a diagram to show, hopefully clarify some of what I talked about setting associations. So this is a very, very simplified example. We start with a Dixel library, which we compiled offline, which contains 3 shader functions. I have a raygen shader, I have a closest hit shader, and I have a miss shader. Obviously, a real application would have probably significantly more different types of shader than this. So then I call some APIs to create a sub-object, which is going to be a hit group. And in this hit group, I say that this is for intersection type triangles. I'm not doing custom intersection. That means that my intersection shader can be null, my any hit shader is null, but my closest hit shader is the closest hit shader that came from my Dixel library. I also have a local root signature, which I created separately using standard Direct3D APIs the same way I would for rasterization. And this specifies the binding convention for how parameters are going to get into my shaders. I now create an association object which links that root signature to my raygen shader. And that says this is the binding of how these things are going to combine. I can also create some configuration objects. These are important for getting maximum efficiency out of the shader compilation. So in the shader config, I specify that the payload size for this thing is going to be 16. That's the payload structure that you heard about earlier that passes information between the different steps in the ray tracing pipeline. I can also specify the max recursion depth. And in this case, I'm saying 1. That means I'm promising up front that I'm not going to do any recursive rays. Configuring this is really important for the implementation to know because it lets the hardware and driver understand how much stack size needs to be reserved for running shaders. Theoretically, ray tracing could recurse an awful lot of times. Hypothetically infinite if you just kept going. Obviously, you would run out of resources and burn miserably if you tried that. But really, you want to stop significantly short of infinite. And if the implementation doesn't know the maximum recursion, it's like, how do you allocate a stack when you have a lot of different shader threads running in parallel on the GPU? Even fairly small stacks get pretty big when you multiply them by the number of shader cores in a modern piece of silicon. So telling the implementation whether you plan to recurse is important. This example, I'm not recursing at all. The example you saw earlier, the recurse count would be maybe 2 or 3 maximum. Then I take all of these sub-objects that I've created, combine them all to call create sub-object. And that's the point where this whole configuration gets handed to the implementation and the driver compiles this stuff down into what's really going to run on the GPU. And now that I've done that, I can call getShaderIdentifier to look up my raygen shader, my hit group, and finally my miss shader, which are the 32-byte blobs which I'm going to go put in my shader record. That diagram is fairly confusing, and I didn't even get as far as the actual code. If you're feeling overwhelmed at this point, here's a link to some sample code that shows you how to do that. I would recommend looking it up. A lot of times, just start with the sample, copy and paste. It's not as complicated as it initially seems. So now we have acceleration structures with geometry in them. We have a set of shaders which have been compiled and linked and populated into shader records that we can index into. So we're ready to call dispatch rays, and this is what kicks everything off and actually makes some ray tracing happen. This is the shortest part of my talk because dispatch rays is a really simple API. It takes one parameter, which is a D3D12 dispatch rays desk, and that's it, you're done. Ray tracing is completed. I should talk about what goes into that desk structure. Most of this should be fairly obvious based on what we've covered so far. So we have the shader record for the ray generation shader that we're going to invoke. We have a table of miss shaders, a table of hit groups, a table of callable shaders, and then we have width, height, and depth, which are how many invocations of this ray generation shader to invoke. Most often, if you're doing like ray tracing for a camera or something, you would have width be the width of the screen, height be the height of the screen, depth be 1. It doesn't have to be. You can do just kind of one-dimensional dispatch if you want to have height and depth both at 1 and just use width. That's totally up to you. Filling in those structures that this refers to. When we say GPU virtual address range, that's just a start address and size. And when we say range and size, that's start address, size, and stride, which is the offset from one shader record to the other. So you can see from this structure that we have just one ray generation shader, because that's where everything starts. But then we have an array of multiple miss shaders and multiple hit groups. And that's it. We have succeeded in doing ray tracing. Before I wrap up, I want to cover a few other small but fairly important details. First off, where do you get this stuff? If you're all excited and you want to rush home and start programming up ray tracing, what do you download? Where do you begin? So this hasn't shipped for real in Windows yet. What is available today is called the experimental preview. This is what we released at GDC earlier this spring. The experimental preview requires the Windows 10 April 18 update. It has to be exactly that build of Windows. It won't run on any other variant of Windows 10. And you obviously need suitable hardware and drivers to be able to support this. The preview is not quite the same thing as the final API. That's why we released a preview. We've been working with partners and responding to feedback and made some changes in response to that feedback. But it's extremely close. Moving content from the preview to the final API is typically a few hours, if not even just minutes of work. And I have a link here to where you can get that. It's on the forums.directxtech.com site. So this is something you can download today, start using. The official release of DirectX Raytracing is coming in the next version of Windows, which is codenamed Redstone 5. That's actually already available through the Insider Preview program. So if you're in the Insider Preview taking flights, you will have access to that. And the Insider Preview SDKs have all the final headers and libs that you need to start using this stuff. The third option we have is the fallback layer, which I will talk about more in a minute. That's an open source project on GitHub. And finally, we have some sample code also on GitHub, which is on the DirectX graphics samples repository. This is a great place to look if you want to see real code that does this stuff for real. We have some samples that do ranging from just kind of hello triangle up to some interesting intersection shaders and dynamic geometry, and all kinds of stuff to look at. The other aspect is checking at runtime whether you actually have support for this or not. And please don't ship applications that just assume that every GPU can do ray tracing, because we're not quite there yet. This is done through the check feature support API. You check for feature D3D12 options 5, and that will give you back a structure that contains a ray tracing tier. And you check for the ray tracing tier being greater than or equal to ray tracing tier 1.0. Obviously, we're reserving room for future expansion here. I assume that we're taking the first step onto a bold new path of ray tracing. And you can obviously imagine that there will be more tiers in the future with more capabilities. Let's talk about the fallback layer. So if you don't have a piece of hardware that can do ray tracing yet, the fallback layer is an option to basically emulate the DirectX Raytracing API via compute shaders. It's mostly complete. It doesn't support a few corner cases like callable shaders, but it can do all of the kind of basics. You can run, build acceleration structures, ray trace against them, do hit shaders, miss shaders, custom intersection shaders. Because it's just a compute, I say just, it's a very, very complicated compute shader, but it is a compute shader that will run on existing GPUs that don't have a new driver or don't have dedicated ray tracing hardware support. It does need a somewhat recent version of Windows 10. The fall 2017 update is sufficient to support this. And it does need a GPU that supports retail Dixel shader model. That's the shader model 6. The fallback layer is a standalone static lib. It's actually open source on GitHub, so you can compile it yourself, but the output of compiling it is a lib that you link into your application. So it's not quite the same API as DirectX. You just kind of redirect it to initialization time. Instead of creating a D3D12 device, you create a D3D12 fallback device, which comes from this lib. But other than that, it's, once you're going, it's very, very close to being the same API. The nice thing about this is it will redirect automatically to the real native DXR implementation if the driver has support. So if you want to bootstrap something using the fallback layer, but then have it run on hardware when you get the hardware, you don't need to scatter your code with if fallback, then call fallback API, else call real API. The fallback layer will do that for you. So just call the fallback layer, and it will pass through. The big thing to be aware of with this is obviously it's not going to be as fast as a true silicon implementation. It's fast enough that you can certainly start experimenting and bringing things up and learning how this shader model works. It's a great thing. Yeah. Start experimenting with it. This is something you can go home today and start programming with. But don't expect to see the kind of performance that you're seeing from some of the demos running on that thing, because it doesn't have that thing. The biggest difference in the programming model when you're using the fallback layer is how GPU pointers work. So compute shaders in D3D12 don't support arbitrary memory access on the GPU, just through a memory address. But when you call build ray tracing acceleration structure, it's full of pointers. Everything is specified this way. So this was the one piece of ray tracing that we were not able to emulate automatically on pointers. The way the fallback layer handles this, it replaces every time that a GPU virtual address occurs. Instead, you pass an index into a descriptor heap plus a byte offset from that index. And that way you can just do indexing in the standard DirectX way. So that means to use the fallback layer, you have to go and create a view around any memory that you want to use for ray tracing and pass that in. It's a small code change. The documentation for the fallback layer gives some good examples of how to do this. This code shows typically how you would do that. You could say, if I'm using the ray tracing driver, then I go create a descriptor handle, then bind that, and create an unordered access view over it. Final thing I want to talk about today is debugging. The Pix tool is our tool for debugging and profiling all of DirectX 12. It fully supports DirectX Raytracing. This is available on the blogs.msdn.com/Pix site. This is a screenshot of Pix's shader table viewer. So that's actually very similar to the table I showed you earlier when I was explaining what goes into a shader table. Pix can show you this from a capture of any DXR application, and it will pull apart what you've put in your shader table, show you the layout and what root signatures were bound and what arguments were bound. I don't know if you can see it here, but you can see there's some little yellow warning signs on a couple of the entries where things are not filled in properly. This is invaluable if you're trying to fill in shader tables and having a hard time getting the right data in the right place. It's a great way to see what really happened. And Pix can also visualize acceleration structures. So this is an example of, in the event list, I've selected a dispatch raise call, and Pix is showing me the geometry of what that dispatch raise was going to hit test against, so I can make sure that I've actually built them correctly and my objects are all in the place I expected them to be. So hopefully that is enough for you to have a sense of how to start using ray tracing. And I have 8 minutes left to take questions.
Hi, so I have 2 quick questions. One, I'm currently using ray tracing within a rasterizer to apply reflections onto geometry that has arbitrarily changing convexity and concavity. Is there any way to trace the rays based on rasterization?
Yes, so deferred rendering is typically the way to do that. So you'd render into a G-buffer and then do a pass over the G-buffer that would trace rays from G-buffer pixels. You can't currently trace rays from inside a pixel shader, so you need to write the pixel shader results out to somewhere and then do a second pass to trace rays.
Okay, and then the second question is, if I have geometry that is deformable and arbitrarily cuttable, is that doable with the BVH, or would it have to handle it similar to what you do with skinning and animation? Or?
So that's a fantastic question. The deformable geometry is kind of the hardest case for ray tracing, because the whole thing that makes ray tracing work is based on taking the geometry up front and optimizing it. So you basically have 2 options here. You can do the deforming as a pre-pass, very much like skinning, and then build a new BVH. That's going to be an upfront cost, but gives you a structure that's very efficient to ray trace against. The other option is to use a custom intersection shader. And once you do that, it's just shader code. You can look up any data structure you like, do any math you like. This can be arbitrarily complex. We tend to think and talk about intersection shaders as being for doing the classic ray-sphere intersection, but they can do so much more. In the extreme case, it is entirely possible that you could ignore all of the built-in BVH intersection, have a custom intersection shader with a bounding box that was the entire world, and you just go and do arbitrarily complex ray intersection math against arbitrary data structures inside that shader. It'd be kind of pointless, and you would not get any of the perf wins of the optimized implementation, but you could do that.
Awesome.
So yeah, if you want to, that's really a perf trade-off. It'll be more expensive to trace against things if you do all of that deformation in an intersection shader, but you don't pay the upfront BVH build cost.
Okay, thank you.
Two very quick questions. The acceleration structure, what sort of like memory footprint are we looking at? Are we looking at like, based on geometric complexity, are we just looking at like big O log n? I mean big O n or n squared or something? And the other question is the compression scheme. What sort of a compression ratio do we get? Or are these both hardware dependent?
They're extremely hardware dependent. So you're talking about memory usage or build time? Or both?
Memory usage.
Okay. So memory usage is pretty much linear with the amount of geometry. Typically, I would expect to be looking at memory usage in the tens up to maybe hundreds, but probably tens of megabytes. A huge amount of this we don't really know yet, and this is one of the things I'm so excited about this stage of ray tracing. Yeah, we have some content, some interesting demos. You're going to see one of them in a minute. But right now, I can count the people who've built high-end content using ray tracing on GPUs on the fingers of one hand. And a lot of that is prototype content. So I'm looking to the people in this room to start using this for real and give us those answers. And my guess is that at SIGGRAPH next year, we're going to have a ton of talks of the form, here's a year worth of learnings about ray tracing and how to use this stuff effectively. Yeah, to some extent, we just don't know yet. As far as compression format, that's completely implementation defined. That's why this stuff is opaque. There are interesting R&D going on at the hardware and implementation level as well as at the API and how to use this level.
What information about the primitives that were intersected is passed into the callable shaders and the hit shaders? Like, do you get the mesh instance index or the primitive index within the instance?
Yes. Yeah, so if it's a standard, using the standard triangle intersection, you get index and barycentric coordinates.
Okay,
and if you're doing a custom intersection shader, it's entirely up to you. You return whatever information you want out of the intersection.
Okay, primitive index or instance index or both?
Both.
Okay, and then is that showing you the that GPU's BVH for? Is PIC showing you what your current setup generated for the BVH, or is that just like a DirectX standard implementation?
This is so the visualizer that PIC shows for acceleration structures is read back from the driver.
Okay.
So it's kind of up to the implementation how much that shows details of the BVH. It's not actually broken down into BVH structure, it just shows the triangles. But in some cases, the triangles that come back don't necessarily exactly match the ones that go in. We'll find implementations do things like folding bounding boxes together and potentially merging planar triangles. And there's a lot of interesting tricks in BVH building that you don't necessarily do the most obvious thing. And some of that you will see in PICs. Yeah.
Okay, thank you.
Great, thank you.
While he's getting set up, the next speaker is Colin is a senior software engineer at Seed and Electronic Arts, which is a cross-disciplinary group working on cutting-edge feature technologies and creative experiences. And he's going to talk about some of his experiences integrating ray tracing into some of the work they've done at Seed. All right.
So hi everyone, and thanks Chris for having me part of this course. And so I only have 20 minutes, so my goal is to give you some insights on how us at Seed have handled this transition from raster and compute to real-time ray tracing with DXR. Like I said, I only have 20 minutes, so I'll try to cram as much stuff as I can, talk really fast, but if you have anything, you can come and see me after, ask questions, no problem. And so if you don't know who Seed is, well, we're basically a technical and creative research division inside Electronic Arts, basically a cross-disciplinary team with a mission to explore the future of interactive entertainment and at the end of the day enable, or the goal to enable people to create their own games and experiences. And so we have offices in Stockholm, Los Angeles, and Montreal. And so one of our recent projects was this experiment with hybrid real-time rendering, deep learning agents, and procedural level generation. And so we presented this at GDC this year, 5 months ago. In case you haven't seen it, here's a quick trailer. So Pika Pika is a mini game that we built for our AI agents, so it's not really for humans to play. And so we use reinforcement learning, and with that, the agents basically learn how to navigate the environment that you see there on the right, and they try to fix those the conveyor belts by fixing the machines there that break randomly. And so if you're interested in the AI part of the paper, we have a paper on archives, so make sure to check it out. It talks about like how we train the agents, what they see, and how they communicate with the game logic. And so we built this mini game from the ground up with our in-house research R&D framework, which is called Halcyon, which is a flexible framework that's still pretty young but capable of doing some pretty cool graphics. We've had the opportunity to be involved quite early with Microsoft and NVIDIA on DirectX Raytracing, and so we wanted to explore what some of the possibilities that were with this piece of technology. And from those visuals, obviously, this is not the typical thing you expect from a AAA company from EA, but we wanted to explore something a bit different and a bit unusual. We wanted cute visuals that would be clean, stylized, but still grounded in physically based rendering. And we wanted to showcase the strengths of ray tracing while also taking into account the fact that we only had 2 artists. And so we use procedural level generation. And so our algorithm basically drives the placement of assets. And so if you want more info on that, you should check Anastasia's talks that she's done. And she explains how the world was procedurally generated. And so Pika Pika runs at 60 FPS on a Titan V at 1080p. And so to achieve this, we built a hybrid of classic rendering techniques with rasterization and compute. You can see the combination of all the various techniques there. And so we sprinkled some ray tracing on top, I guess you could say that. And we take advantage, basically, of rasterization, compute, and ray tracing. And so to be able to do this, we need a pretty standard deferred renderer with compute-based lighting. And we also have a pretty standard, full-fledged post-processing stack. So for example, we render shadows with ray tracing, or we also support cascaded shadow maps. The reflections can be ray traced or screen spaced ray march, and the same thing with AO. It's only GI, translucency, and transparency in our demo that absolutely requires ray tracing. And so, the goal of this presentation basically to provide you with some tips and tricks and how to evolve your engine from being raster and compute only to supporting ray tracing with DXR. And so I'm hoping to give you some really practical insight, on bringing these easy to do, I guess, between quotes, like core ray tracing techniques to production, but also warn you about some of the challenges you might face as you go through this really awesome transition. And so one question you might have is, well, I'm a developer and I want to take advantage of DXR, so what should I do? Well, there's pretty many things you can do. So first, the transition will not be automagical. Some effects and techniques are easy to add, like you're going to see, but like hard shadows or hard reflections or AO. But it starts to get a bit tricky when things start to get blurry. And so the thing is, most ray tracing techniques from books assume offline ray tracing, like perfect ray tracing. And so there's still some work to do there if you want to adapt some of those techniques for real time. And so this means you need to embrace, like upfront, you need to embrace filtering and adapting techniques to the constraints of real time. And that said, from the previous talks you saw in this course, the API is pretty intuitive, and out of the box it's really easy to get something going, so that's really neat. So it should be really easy for you to get it up and running and implement stuff and really improve quickly. And so if your engine already has a good DX12 implementation, then your job should be pretty easy. But so one thing to note is that you really need like a good grasp on your resources, like Sean said, and because you need to have those shader tables and those acceleration structures ready up front for ray tracing. And so some warm up might be required, some stretching. And so let's warm up a bit. And so the first thing you might think of doing is, you might want to brush up a bit on the DirectX Raytracing. Like this course is pretty good, but there's also various open source frameworks that are out there. Falcor, for example, the Microsoft samples. You could also check our GDC and Digital Dragon talks, and you should also check out yesterday's presentation from Matt Farr on adopting lessons from adopting lessons from offline ray tracing to real-time ray tracing from the Advances course. It was really good. He talked about managing variance and noise, really important. And so let's get practical. So first, you'll need to break down passes so that code can be easily swapped in and out. And by that I mean you basically can reuse code between the various stages. And so with HLSL, it's easy because of the interop between raster, ray tracing, and compute. So you'll have to start building these shared functions that you can call from any stage. For example, like material evaluation, lighting code, and various helpers like that. And so also one thing that really helps is making sure your engine can really toggle quickly between techniques. And so this is really essential for comparing, cutting corners, optimizing between proper ray tracing and the real-time ray tracing that you're going to get in the end, and balancing, for optimizing, balancing ray counts. And so preparing passes to be able to swap inputs and outputs as well is going to be really important. So for example, you should break your shadows into a full screen mask so that you can easily swap that. You can easily swap, for example, cascading shadow maps and ray trace shadows. The same idea could apply for like other techniques like screen space reflections and the ray trace reflections. And so obviously there are a few techniques you should implement first, and those are obviously, or should give you the most bang for the buck, and in that difficulty order. That could change, but for us it was shadows, then ambient occlusion, then ray traced reflections. Just adjust something here. All right. And so You know, ray trace shadows are great because they perfectly ground objects in the scene. And like I said, it's not too complicated to implement. You saw from the previous talks, like you just launch a ray towards the light, and if the ray misses, well, you're not in shadow. And you know, while hard shadows are great, soft shadows are definitely better for conveying that scale, and they're definitely more representative of the real world. And so those can be implemented by sampling random directions in a cone towards the light. And so the wider the cone angle, the softer the shadows get, but the more noise you also get. And so you'll have to filter it. And so obviously you can launch one ray. You can launch more than one ray, but that'll require some filtering. And in our case, we basically reproject the results in a TA-style fashion and accumulate shadows and variance. And then we apply a slightly modified filter, a slightly modified SVGF filter, which we modified to be a bit more responsive for shadows by coupling it with a bounding box clamp that's similar to TA. And so this is based on Marco Salvi's variance-based bounding box method, which uses a 5x5 kernel estimate for the standard deviation in the frame. And then, you know, but the results are not perfect. I don't know, maybe you can see them on the video here, or you can see them on the slides after. The slides have the video, but, you know, artifacts aren't really that noticeable with full shading. And so, like I said, another technique that maps well is, of course, ambient occlusion, which we apply to indirect lighting. And so being the integral of the visibility function over the hemisphere, we definitely get some really nice grounded results because of the random directions that are used during sampling. And the fact that they actually end up in the scene, unlike screen space techniques where the rays can go either outside the screen or, you know, some hit point that's just not visible. And so just like in the literature, this is done with, you know, your good old cosine hemispherical sampling around the normal. And in our case, we launch rays from the G-buffer normal, and we use the mesh shader to figure out if we fit something, just like the shadows. And, you know, just like the shadows, you can launch more than one ray per frame. But even with one ray per frame, you should get some pretty nice gradients after a few frames. And we apply a similar filter than the one for the shadows. And so just like AO, the ability to launch rays from the G-buffer allows us to trace pretty cool from smooth to rough reflections. And so we trace them at half resolution. So for every 4 pixels, you get one reflection ray. So that's about a quarter ray per pixel. And then at the hit point, the shadows will typically be sampled with another ray. So that totals to half a ray per pixel. And so the thing is, this works for hard reflections, but you know, you need to support arbitrary normals and varying roughness. And so our approach first combined this with the screen space reflections for performance, but in the end we just ended up ray tracing for simplicity and uniformity. And we've talked about this extensively at GDC and Digital Dragon, so make sure to check out those talks. But if you haven't seen those talks, I'm just going to give you a high level, you know, not going into too many details, but a high level of how the reflection pipeline works. And so first we start by generating rays with BRDF importance sampling. So this basically means that the rays follow the properties of the material. Then, like I said, scene intersection can be done either via screen space reflections or ray tracing. And like I said, in the end, we only ray trace, but we support both. And so once the intersections have been found, we proceed with reconstructing the reflected image. And so our kernel reuses ray hit information across pixels. So we upsample at full resolution. And we also calculate some useful information there that we use during the temporal accumulation pass. And finally, to kind of clean up the last remaining noise, we have this last chance cross-bilateral filter. And so, like I said, in the end, we just use ray tracing for that. And so if you look just at the reflection, this is the raw results you get from one ray every 4 pixels. So it's pretty noisy, as you can see. And this is after spatial reconstruction. Starts to look like something. And then followed by temporal accumulation. and then followed by our bilateral cleanup that kind of removes some of the remaining noise. It kind of over blurs a bit, but it's kind of needed for the rough reflections. And so if you compare this to SSR, and for those of you who implemented SSR, ray tracing is a bit trickier because you can't really cheat and have that blurred version of the screen for like that pre-filtered radiance information. And so we definitely get more noise with than SSR, and so our filters need to be a bit more aggressive. But so to prevent over blurring, we have this variance estimate from the spatial reconstruction pass from before, and we use it to basically scale down the bilateral kernel and the sample count. And in the end, well, we apply temporal A because temporal A is magical, and we get a pretty clean image. And so, you know, considering this comes from a quarter ray per pixel per frame, and you know it works with dynamic camera and object movement, I think it's quite awesome what you can do with just reusing spatial and temporal data. Like if we go back to the raw ray trace output, like yeah, there's a bit of a difference. And so, you know, in the case of reflections or any other technique that you want to implement with hybrid rendering, it's also key to compare against ground truth. Like it's fine to cut corners, but at some point, you know, you still need to validate that what you're doing is right. And so internally, we've built a path tracer that acts as our ground truth, and this is in engine. And so we can basically toggle it whenever we're working on a feature. And we actually use this constantly when working on Pika Pika. And so because of, you know, interop, it's where there's minimal to almost no maintenance required because it's the same shader code that's shared, like all those shader functions I was talking about. You know, having a ground truth comparison tool in your engine shouldn't add too much work. And so this is what it looks like if we toggle the path tracer and wait 15 seconds. The image is nice, but there's some noise. Yes, some of you can see the sparkles there from some of the fireflies from the difficult light paths and the caustics. And you know, compared to our hybrid approach, which runs at, like I said, 60 FPS on a Titan V, it's not quite the same as the path trace version. There's some missing caustics and like some small scale inter-reflections. But overall, you know, it looks pretty decent to me. And so, you know, if we continue talking about some practical things, so make sure to take advantage of that, you know, DirectX interop where you can easily share code and data and results between the stages. Like for example, you know, you can evaluate your HLSL material shaders from the ray tracing stage, which is quite convenient, so there's no conversion required. Some of you might have done in the past with an external lighting tool or whatnot. And you know, actually you should be taking advantage of each stage's strength and so that you can build this really awesome hybrid pipeline. So for example, you can prepare arrays to be launched and trace them on another GPU. This is what we do for GPU support. You can write to a UAV and then read that in another stage, like a ray tracing stage. So, you know, in the end, interop basically allows you to solve these new sparse problems that, you know, with ray tracing as a new tool, you know, that's available to you. And, you know, it makes even more sense these days, and interop will kind of become even more your new best friend, or your best friend again. And so here's some additional practical tips and tricks when working with the XR. And so since you'll be launching many arrays, and as mentioned by Chris, you know, the importance of minimizing what, and Sean as well, like the importance of minimizing what each array carries can definitely influence performance. And so depending on the kind of arrays you're launching, you can have different kinds of payloads, some leaner than others. So like on the right, I think that's our standard lighting payload. So we have all the variables there with some getter and setter functions. And then you can see the shadow payload there, which is, you know, much simpler. And so, yeah, being lean there is kind of important. Another thing is embracing lean recursiveness. You know, make your performance, like make your IHVs happy by not having like infinite recursiveness. Often you don't need it, but you know, try to be nice to the IHVs. And so another thing is, so you can use shader spaces to organize your data. You know, I haven't seen many people use shader spaces, but it kind of makes it useful in case you want to keep things organized, especially if you want to update things at different frequencies. So for us, like we use two spaces where like space 0 is kind of the default space and the static data is there, and space 1 is more like the ray tracing space or where the instancing data resides. And so, speaking of rays and performance, like handling coherency is really key for real-time ray tracing performance. And so obviously you're going to get some adjacent rays that are going to perform similar operations, memory accesses, and they're going to perform well. And while you're going to get some other ones that might trash cache and affect performance. And so depending on which techniques you decide to implement, you'll have to keep this in mind. And so use rays sparingly and trace only when necessary. And so tuning rays and the count of rays to importance and adaptively is really key. And so also make sure to set the max recursivity on the state object, the shader state object. So that's one thing that's really important. And so right now in HLSL, there's really no way to specify up front if a ray you're going to launch is going to be coherent, incoherent. And so providing hints to an IHV, could be good. And who knows, maybe we'll be able to do this in the future. And so as the API keeps evolving, but it's not there yet, but we'll see. And so, as you saw from our work, reconstruction and denoising is really nice. It allows you to get some really great results. And so taking advantage of spatial and temporal domains really will make a difference for you. And there's lots of great work in that field already, and there's still a lot to do. And another question you might have is, well, what about like texture level of detail? And like in the raster world, like MIP mapping is the standard method to avoid texture aliasing, and this is supported by all GPUs, via shading quads and derivatives. The thing is, with ray tracing, as many of you are aware, we don't have shading quads, and so traditionally what people have done in offline is they've used, and many of you probably know this, but they've used ray differentials. And the thing is, now if you're going to compute ray differentials, you kind of have to store those somewhere, in your payload. And so having a heavier payload, and in the case of ray differentials, it could mean up to 12 floats, and you need to carry those down and update those. That can affect performance on top of the other stuff that I showed that we have in our payloads. And so that's the kind of stuff you could potentially optimize. And another alternative you might have is, just sample MIP0. But if you've shipped any AAA game, you know that you can't just sample MIP0 like all the time. It just doesn't work. And so, and also MIP0 will lead to aliasing. Like that's why we have MIP mapping. It gets rid of that sort of stuff and additional performance costs. And so, together with NVIDIA research, we developed a texture LOD technique for ray tracing, which is not perfect, and so we barely scratched the surface, but it's based on the properties of triangles, curvature estimate, distance, and incident angle. And so we get similar quality to ray differentials with a single trilinear lookup, and we only store a single value in the payload, so that's pretty cool. The paper is going to be in Ray Tracing Gems, and there's a preprint available, so if you want, you can check it out and send us feedback. It's kind of an example article, so if you wanted to submit Ray Tracing Gems, that's the kind of format you could submit an article to. But so I was saying, like, we barely scratched the surface, like, so in our case, we still need to look at anisotropy and dependent texture lookups, and when you have these massive shader graphs, it gets a bit more complicated. Also, our technique assumes static UVs. So, we need to, what if you need to recompute those coordinates on the fly? And so we use this for Pika Pika, but the difference was kind of minimal because of the super clean visuals. Even with the detail normals on all objects, with a ton of TA and all that filtering, it was fine. Yeah. And so make sure to check out the paper. And so, this is kind of just a glimpse of some of the stuff that you may have to tackle, and obviously, I think we've done some pretty cool stuff, but we're far from having solved everything, and we still have a lot of work to do. There's a bunch of open problems that we need to tackle together in the years to come, so I think this is really awesome. And check out my HPG keynote if you can, where I go into detail about some of these topics. And hopefully we're going to see, with ray tracing now being so accessible to everybody, some great collaborations between offline ray tracing experts and the game industry. And so, to wrap things up, ray tracing is nice because it kind of makes it possible to replace those hacks that we had and kind of unify things a bit more and kind of phase out some of these screen space techniques that are kind of artifact prone. And out of the box, ray tracing is great because it enables higher quality visuals without painful artist time. But the thing is, there's no free lunch, and so you'll need to put considerable efforts into reconstruction and filtering, like I said. And so with the ray tracing hardware and the possibilities that enables, this is even more awesome. And so tomorrow I'm going to give some performance numbers of PKP running on the new hardware compared to a Titan V during the real-time ray tracing session in the morning. So make sure to attend if that's of interest. But don't forget that ray tracing is just another tool in the toolbox, and it should be choose to use it wisely when it makes most sense. And I think it's very encouraging that we can get, approach the quality of path tracing with just almost 2 rays per pixel, like in the context of Pika. And I'm looking forward to see what you do with ray tracing and take advantage of hybrid rendering with raster compute and ray tracing. And so see you at the NVIDIA real-time session, ray tracing session tomorrow. Like I said, I'm gonna talk about Pika performance on the new Turing architecture, as well as some additional experiments we did, such as ray traced soft transparent shadows. And before I'm done, academia always asks for content from the games people, and often, we don't really give it out. And so for Pika, we have decided, I think it's the first time in the history of EA, to release all the assets from Pika. So you can download them on Sketchfab or on our website, and you can use them for research for free. Build your hybrid ray tracing pipeline, and compare it to ours, and challenge accepted. And so yeah, please use them as much as you want. And so I would like to thank Chris for inviting me in this course, and would like to thank the Pika team back in Stockholm and Los Angeles and the following NVIDIA people for all of this. And I will be taking questions. Thank you.
Hello, Colin.
Hey.
You talk about ghosting. How do you avoid ghosting from temporal accumulation for refraction and shadow arrays? Because I kind of remember for Frostbite you have paper about how to avoid ghosting in SSR.
Yeah.
I wonder if you do the similar things.
It's the similar variance calculation that Tom presented at SIGGRAPH 3 years ago. And there's some additional tricks. So like the Marco Salvi color clamp bounding box really helps with that. And the thing is with denoising, like the more you specialize it around a specific term that you want to monitor variance across, then that's the way to get the best results. So right now, there is no one solution to just just throw this denoiser and everything is just magically going to be perfect. So I don't know if that answers your question or...
Okay, thanks.
Yeah, cool.
Hello, thanks for the talk.
Cool.
So you mentioned at some point that, of course, coherent rays are more efficient. So did you investigate anything related to ray sorting? Like for multiple passes, if you're doing direct bounces?
Yeah, no, we didn't look at that, but definitely in the future, that's something we want to check out for sure. Yeah.
Thanks.
Sorry about that. Thanks.
Hey, since you're launching rays from the G buffer, did you actually have any issues with self-intersection?
So we did, and so what you need to do is in your ray description, you can define Tmin and Tmax right? And so that's when that T-min value kind of becomes a bit of a challenge. And so there's some things you can do with like view distance to objects. You can like fiddle with it. We don't have the perfect, and it's like per technique specified, but usually it's not a problem. But it does happen. So we've done stuff for shadows, like we tweak that number based on how close you are from the surface.
Thanks.
Cool.
Salut.
Cool.
Within the lifespan of a ray, where have you found that you can see more bottleneck, or it's hard to say?
I think it really comes down to coherency. Like, you know, if you're gonna trace primary rays, you know, just to figure out like, oh, or like, yeah, just primary rays, you're not gonna get, you know, it's pretty efficient. It's when you start launching these rays that go in all sorts of directions, that hit all sorts of materials, that's when it becomes a bit challenging. But, you know, obviously our scene was kind of super simple, and in the future we want to explore different kinds of scenes with like more content. And so I think if you ask me that question in a few months, I'll give you a better answer.
Thanks.
Cool. Hey.
So have you tried ray tracing with animated meshes?
Right. So the little robots right there, it's basically just the top acceleration that updates, right? We kind of cheated a bit. They're not skinned. And yeah, in the future, definitely this is something we want to check out a bit more, like, you know, bigger worlds with more animated stuff. So I can't really give you some.
Is there anyone who has tried?
Well, so there was that
epic
demo last year with the Star Wars characters. So you might want to ask those guys how that. I know they were pretty high poly, so you might want to ask them.
They looked a bit like rigid meshes,
right?
Because there were stormtroopers.
Yeah, I mean, there's still a lot of stuff to do, and you know, some of the open problems do include. Did I write it there? And well, animated meshes. It's interesting. Cool. Thanks. That's it. Thank you very much.